Okay. Hello, everyone. Welcome to the session of functional materials for energy storage and conversion devices. As we all know, this conference has been postponed for 1 year due to the pandemic. But I'm really glad that it's happening today, and it's my pleasure to be the moderator of this session. I hope we can spend some wonderful time on the presentations. My name is Weibing Chu. I'm a postdoc at the University of Southern California in Oleg Prajito's group. Today, we are going to have 10 speakers in this session, and I would appreciate if the speaker could pay attention to the time constraint when giving presentation. I can also help giving reminder when time is up. Okay, let's get started now. Let's welcome today's first speaker, Professor Rajapaksi from the University of Peradeniya. Professor Rajapaksi, could you unmute?
Yeah, I'm Professor Rajapaksi. Thank you for good introduction. My screen share has been paused.
Sorry,
my screen sharing is paused.
Yeah. Could you reshare your screen?
Yeah, that's what I'm going to do. I'll open again. So it says your screen sharing is paused. So
I cannot see your screen.
I'll stop here. I'll try to do it again. It doesn't come.
Let me make you cool.
You get it now?
Yeah, cool. Yeah,
everything
looks good.
Right. Sorry about this technical problem. I'll try to keep my 10 minutes time. I'm Professor Rajapaksi, and we are talking on water photo splitting for hydrogen generation using transition metal ion or lanthanide doped titanium dioxide nanoparticle based photon up conversion materials. And as you know, the energy demand, the rapid increase in global population has led to a drastic increase in universal energy consumption. Estimated growth of world energy consumption is 28% between 2015 and 2040. Approximately 90% of global energy is fulfilled by fossil fuels, and other 10% is supplied by nuclear, wind, hydropower, geothermal, and hydrogen. So you see this US energy consumption by energy sources in 2017, almost 37% is petroleum. So, however, there are other like hydroelectric 25%, biomass, biofuel, wood accounts for 45%, wind 20%, solar 6%, geothermal 2%, likewise. So why hydrogen? It's the cleanest and renewable energy source. The combustion yields heat and water. You know, this reaction between hydrogen and oxygen is highly exothermic. Delta G is minus 237 kilojoule per mole. And if you compare properties, hydrogen has gross heating value megajoule in kilogram, megajoule per kilogram, between 120 to 142, whereas methanol has the value between 50 to 55, gasoline between 44 to 46. Simply, hydrogen is very, very light, and the gross heating value is very high. And hydrogen production, so this is source US Department of Energy Office of the Energy Efficiency. This is in the public domain. So natural gas reforming is the established industrial process. Then biomass gasification, and then cold gasification with the electrolysis, electrolysis using solar, and high temperature electrolysis, photoelectrochemical cells, photobiological likewise. So these things are now actually emerging technologies. So discovery of photocatalytic materials, credit goes to Professors Fujishima and Honda. They noticed that when irradiated with light, titanium dioxide absorbs the energy that enables the decomposition of water into hydrogen and oxygen. So Fujishima published his work in 1972 in the journal Nature. The new phenomenon named after his discovery as the Honda-Fujishima effect. And mechanism of photocatalytic water splitting. Obviously, when you take semiconductor like titanium dioxide, it has band gap of 2.3 electron volts, and nicely conduction band edge, bottom of the conduction band is above the strand electrode potential of H plus H2, which is 0 electron volt, and the top of the conduction valence band is below the oxygen hydrogen potential, at least on platinum 1.23. So the bands match very nicely. So when titanium dioxide absorbs the energy in the UV, like 380 nanometer radiation, it creates electrons electrons get excited to the conduction band, creating a hole in the valence band. These electrons are energetic to reduce H plus to hydrogen and to oxidize water to oxygen. The overall process is 2 water liquid plus 4 holes and 4 oxygen gas plus 2 hydrogen gas. And if you see, I mean, these are the band gap is greater than 1.23, and these are the conditions. Conduction band should be more negative than the H plus H2 electrode potential. Upward is negative potential, downward is positive potential. Valence band should be more positive than the water oxidation potential, and photocorrosion resistance. Comparing all these properties, there are a lot of semiconductors that fall into that category, but titanium dioxide anatase form is the best because it is photocorrosion resistant also. So why titanium? Energy levels are appropriate to initiate the water splitting reaction, chemical stability, high natural abundance, cost effectiveness, environmental friendliness, tunable electronic energy band gap, and non-toxic material. However, there are some problems. So therefore, we tried dope in titanium dioxide with lanthanide ions and some transition metal ions, and with some metals like silver. So what are the problems? The fast charge carrier recombination, inable to harvest visible light because it band gap is too high, visible and IR radiation of the solar spectrum, and to generate 3.2 electron volts, it requires a wavelength of 387 nanometers. So how to overcome these problems? Noble metal loading, anion doping, metal ion doping, cation doping, dye-sensitization, and composite photocatalytic materials. So we are dealing with this metal ion doping, where we selected these lanthanide ions and some transition metal ions. So lanthanide ions have F orbitals, and they have the ability to up-convert near infrared radiation into visible radiation. So for electronic excitations, you need visible UV radiation, although you have 55% IR in the incident solar spectrum. So IR cannot give electronic excitation. So what you have to do is to adapt several photons. In second lecture, I will explain that. Adapt several IR photons and make visible photons by the process called photon up conversion. So when you dope this titanium dioxide with iridium-4, erbium-3, ytterbium-3, niobium-5, palladium-2, etc., you can up-convert this infrared radiation to visible radiation. So by having, so this is an example. We have done all this work. So iridium-4 doped and silver metal deposited TiO2. So we have characterized this using XRD and all these peaks by this color is anatase, and this is silvanate, and these green ones are iridium oxide, and these purple ones are silver oxide. So you have these materials in it, and XRF also shows the presence of these elements. And as you see from the UV visible infrared spectrum, it absorbs all the way through, very high absorption in UV, visible, and in NIR also, somewhere around 1,000 nanometers. So that means it can harvest UV visible, and this IR radiation has to be upconverted for electronic excitation. By doing so, we have overcome all these problems. So we have metal oxide, UV, visible, and IR all can be harvested. So water is not a good oxidant. So we can use a better oxidant like sacrificial methanol or ethanol, so that the whole can be sort of successfully scavenged to make. So if you use ethanol, you get acetaldehyde and 2H plus, and electrons can reduce H plus to hydrogen in an efficient manner. So, and that solves the problem of separating two gases, hydrogen and oxygen also. So in my last slide, I show you some sort of experiments that we have done with this catalyst. We just coat that catalyst on glass and put in water and irradiate with the whole spectrum, and also with IR, you can see hydrogen generation. So this is iridium doped one. There's another one here. You see with copper doped one also gives hydrogen just by, this is just to demonstrate, just when you irradiate with visible light, it's all whole spectrum OIR, you can get hydrogen. But of course, with the IR, you get the rate is very low. So the catalysts were actually these. You see hydrogen generation when we just shine with light. We have characterized all these catalysts with XCM, XRD, and many other techniques. And due to very limited time, I'm not going to go into details. And we can, as long as we have ethanol, the hydrogen production keeps on going. And thank you very much. And I would like to entertain any question if you
have. Thanks, Professor Rajapakse. It's really an impressive talk. Since it seems we missed two presenters, maybe we can have some question Q&A section. Meanwhile, I want to double check, is Professor Eugene Harfis here from the Russian Academy of Science? And also the Professor Stefano Agoni from the University of Padua here. Professor Eugene Harfis and Professor Stefano Agoni, are you here? Okay. So, Professor Rajapakse, would you mind give your second talk right now?
My second talk, yeah, that's very nice. Right, I'll.
I have a question about the previous talk, if I may.
Sure, go ahead.
What kind of dyes did you use in your work?
No dyes. This is just the transient metal low lanthanide iron doped GiO2 just in water with ethanol in there. There's no dye in here.
Okay, no dye sensitization. Right? Okay, thanks.
Right. So I can do my second presentation straight away now. Again, on up-converted infrared radiation for dye-sensitized solar cells to perform in the dark, actually now. So we use up-converted infrared radiation or dye-sensitized solar cells to work in the dark. Myself and my student Asita and my colleague Professor Ashoka Kumar are the contributors of this paper. And recording කිව්වහම start වුණා recording. ඒක resume කරන්න ඕනේ මොනවා හරි කරන්න. So infrared upconversion. So solar spectrum add or remove buttons ඒකේ recording කියලා තමයි එන්නේ. Sorry. A solar spectrum incident on the Earth's surface consists mainly of 5% ultraviolet, 40 to 45% visible, and 50 to 55% infrared radiation. However, dye-sensitized solar cells, DSCs, only utilize UV and some visible components, but not the major IR fraction, 50 to 55% infrared fraction, since IR is incapable of electronic excitation. IR radiation cannot excite electrons. So in order to utilize IR radiation, these IR photons have to be added to get UV or visible radiation via the process known as photon upconversion. So in the photon upconversion, you see that this is ultraviolet region and visible region is exaggerated, although compared to an ultraviolet region that goes far beyond several large region. Visible region is only very small, from 400 to 750 nanometers, and then you have large infrared radiation incident on the Earth. So what you do is we excite this upconversion nanoparticles using infrared radiation. They add these photons and produce emission in the visible or UV. So that is, to explain it very simply, consider an electron. So this is a visible to visible upconversion I'm explaining here. Consider an electron that is in the ground state, denoted by 0 here, and is excited to first level by an absorption of radiation H-nu. And then another H-nu excites that electron from the level 1 to level 2. On the way back, you can add up the two H-nus, you can get H times 2 nu. So basically you have multiplied nu by 2. If you have several levels like in a ladder, you can absorb n number of H-nus and get H times n nu. So when it reverses back to its ground state, visible light is emitted. So here what you're showing is two red photons adding up to get a blue photon. So you can see that in the news FESC-2. So this is the site where you can get that. And what we used here is upconversion nanomaterials. They consist of a host lattice, sodium, yttrium tetrafluoride, with lanthanum ions, different lanthanum ions, lanthanum 3+ ions door. Here in this illustration, sodium and yttrium ions are denoted by blue and green, and small fraction of lanthanum ions by red. So for example, if you use yttrium and europium 3+ ions, so yttrium you can excite from there, from this 3F702 to 2F502. 2F702 by an absorption of photon, and then it can transfer. Iridium also can do transfer. They are likewise. So the iridium gives several energy levels for which these photons to go up, and eventually they can come down from higher levels to lower level, up converting this radiation to different visible photons. So system 1, we tried the earlier system with system 1 is the earlier system that we tried with transimetal ion doped titanium dioxide and lanthanum doped TiO2. However, we found that the performance of the liquid electrolyte-based dye-sensitized solar cell is inferior to one without upconversion crystals, even with one sun illumination. I'll give you the results. And it did not give any efficiency with infrared illumination alone. If you used transition metal ion or lanthanum ion doped TiO2, as I described in my previous presentation, although it is helpful in making hydrogen, it's not good for liquid electrolyte based dye-sensitized salts, mainly due to when you shine with infrared radiation, a lot of heat is generated. So this is mainly due to evaporation of the volatile solvent that is acetonitrile that is present in liquid electrolyte based DSC. The electrolyte contains iodide, triiodide dissolved in acetonitrile, so it gets evaporated. So the solar cell gets dried down. So these are the results. The efficiency of the dye-sensitized solar cells prepared with the system 1 containing upconverting dopants in TiO2 nanoparticles. TiO2 only solar, when used TiO2 only without any doping, TiO2 only with dye N719 dye, you get 8.1% efficiency with one sun, but with IR radiation, you don't hardly get any efficiency. Iridium, europium, holmium, niobium, samarium, iridium 4, and europium 3 with silver, all these gave inferior performance compared to TiO2 only DSC. So that is because when you introduce energy levels in between, there's very good chance for the photoexcited electrons to recombine. So recombination is one of those problems. Even that is why even with one sun irradiation, you are not getting better efficiencies than what you expect. Even if IR is upconverted, more electrons are excited, but most of the electrons get recombinated. So solid cells, when you use, another problem is when you shine with IR radiation, most of the liquid electrolyte gets evaporated. So even the TiO2 only cell gives you 0 efficiency. But we can use solid type dye-sensitized solar cells where the liquid electrolyte can be replaced with the P-type semiconductor, which is the whole conductor. What we use was P-type Key-plus iodide. P-type Key-plus iodide semiconductor. So obviously due to the inferior diffusion and ionic transport, the efficiency of solar cells when you use a P-type semiconductor is lower than that in the liquid type one. But 4% efficiency with TiO2 only is fairly a reasonable result for a solid cell, because a solid cell is more durable because there's no liquid, there's no leaking, no evaporation. So we get 4% efficiency with one sun irradiation. But however, the efficiency is much lower when you use instead of titanium dioxide, when you use this lanthanide doped TiO2. Efficiencies are much lower. This is due to recombination. So these ions introduce the ladder of energy levels where the excited electron in the conduction band can drop in and then recombine. So with IR alone, again, you did not get any efficiency with this system. But what we were not actually sort of unhappy with that, because having learned that, we want to try a system that would work. So we tried cuprous iodide or conductor-based DSAs. For the first time, we use a lanthanide crystal. So instead of doping with the transition metal ions or lanthanide ions, we use sodium yttrium tetrachloride doped with lanthanum ions together with the dye. So we use bare titanium dioxide. So we have N719 and the upconverting crystals we coated on TiO2. So we have coated dye N719 as well as this upconverting lanthanide crystal, that is various lanthanide dye doped sodium yttrium tetrachloride, which I showed you earlier. And we used them with, we tried with liquid electrolyte base, iodide, triiodide, and acetonide electrolyte, and all solid state type solar cell utilizing P-type cuprous iodide whole conductor base DAC. So again, the liquid type DAC did not perform with infrared illumination in the dark. However, the cuprous iodide whole conductor base solar cell gives appreciable efficiency with of 4.5% with one sun illumination. So 4.5 is fairly much better. So in the absence of this upconverted nanocrystal, we saw only 4%. Now 0.5% increase. So, and also we tried this system with IR alone, with the intensity of the IR radiation is much lower than that of one sun, but yet we get 0.4% efficiency. So that increased efficiency is due to upconverted infrared radiation. So for the first time, we have shown that the solid state cell works in the dark with upconverted infrared radiation. So in the dark, in the night, we are in the night now. So here we have enough infrared radiation. So you can use that infrared radiation to for solar cells to work. We have demonstrated, although we got very small efficiency, and we have now got a research grant from the US Air Force research to work on fundamental aspects of these upconverted materials and don't accept a type of electronically conducting polymer core shell structures. So don't accept a type of polymers. I will discuss in my invited lecture tomorrow. So for the first time, we show that the sensitized solar cells, when you have these upconverted nanocrystals, can work in the dark without visible and UV radiation, in the dark with upconverted infrared radiation. So we make this, this is TiO2, should be made. We have made these plates with a different method called drop casting. We have to deposit on it, and then little by little at height, and then what's happening?
Thank you, Professor Rajapakse. This is a really impressive talk. I think we still have time to take one question. So, any question? All right, let's thank Professor Rajapakse again. Our next speaker is Professor Mamoon Bader from the Artificial University. Let's Professor Mamoon, would you mind start sharing? Professor Mamoon, you are muted.
Okay, I'm sorry. I did unmute myself. Good morning, everyone on the Pacific Coast and East Coast as well, and good evening to all our colleagues elsewhere. First of all, I'd like to thank the organizing committee for their tremendous work with all the changes with the COVID and what should be a straightforward conference. I'm sure this has been unusually difficult for almost like 2.5 years. So I sincerely thank all of you. I'd like to thank our Trojan colleague, maybe Professor Chu. And I would, is it easier to start with sharing the screen? Is that fine?
Yes, please.
Okay. So I share the screen. Let me just make sure that I have that. All right, so my talk to you today is about structural, electrochemical, and optical properties of small organic molecules for solar cell applications. I sort of came to this field from the back door, so to speak. I did my PhD at USC with Larry Dalton in nonlinear optical materials. And then I became interested in two-photon and multi-photon absorbing materials. So basically the idea is we synthesize these organic conjugated molecules, oligomers and polymers, and then we look at their nonlinear optical properties. So I was visiting a good friend of mine, Professor Mike Ward's group in 2000 or in 2001, I believe, summer 2001. And we looked at the crystal structure of some of these materials. They crystallize. So I said, okay, I was waiting for a machine to be fixed, and I started doing some X-ray crystallography. And the first molecule we did, I'll go through straight to that, what I call the lead compound, is this molecule here. I just to share with you exactly the history of this. So it turns out this is a rather small molecule. And the thiophene units, or the thiophene molecules, crystallize with sulfurs on both on the same side, or what we call syn configuration. So I had a box of about 30 some compounds similar, and we solved as many structures as we could. And it turns out we learned a little bit about when do the sulfurs can come to one side to another. Then Jean-Luc Berda at Georgia Tech published a paper in JACS, I think in 2006, looking at some of these, what's the difference in terms of electron transport, and when you have an oligomer with the syn versus anti configuration of these molecules. So that was the beginning of my interest in this area. So what you see here is just pictures of some of these crystals. They're fascinating, these molecules. I became all of a sudden interested in crystal structures and how does that impact the efficiency of these of devices made from these crystals, how the two molecules get together, basically. I became interested in that. Very fundamental, simple question. How do they get together? How far can we play with how they stack in the solid state, and how does that impact let's say mobility and field effect transistor configuration? We did some work with the Dan Frisbee group at the University of Minnesota. So some of these crystals you can see shiny. I don't know, the physicist in the room probably can correct me. Shiny for me means some free electrons. Is that an approximate good approximation? I don't know. But shiny, you can see your face actually in these crystals, almost like a mirror. And these are organics. I'm sorry.
Professor Mamu, would you mind making it a full screen?
Oh, I'm sorry. I have to control the full screen, of course.
Okay.
How do I go to full screen? Just 1 second. Okay, let me just, I think I have to do it from the PowerPoint, right?
Yeah. I think it's just in the slideshow. Or you can press F5.
F5?
Yeah, F5.
Just give me a second, please. I'm sorry, I'm not too...
No worries.
Excuse me,
Take your
doctor.
time.
Yes.
There is option at the bottom. You can just press that one.
Let me just see how I do this.
Apply thing at the bottom.
Is this better now?
Yes, thank you.
It looks
Thank
good.
you so much.
Okay, so I apologize for that. Basically, what we have done is we look at these crystals, and you can see that many of them are really, shiny, and these are small molecules. That became surprising. So we attributed that to some free electrons in these molecules, and we started looking at easy chemistry. I was at Penn State Hazleton, which is an undergraduate institution of Penn State University, and mostly I have access to undergraduate students. I didn't have graduate students to work with me, so we tend to work with simple chemistry that can be done by undergrads. So what I did is I looked at what else can we work with. So this is thiophene. Thiophene, you can think of it as, for those of you who work with organic synthesis, is like an activated aromatic compound. It's just like phenol, okay? So it reacts rather directly. So we started looking at other molecules, such as this molecule, triphenylamine, which is a whole transport material. And we got quite a few interesting results. And I will go through just the introduction. I'm sure most of you are familiar with conjugated molecules, whether poly 3-hexylthiophene or pentacene. Pentacene was the molecule to beat in organic chemistry at that time, in organic semiconductors. So, and the applications and what kind of mobilities we were interested in. So we became interested in synthesis and crystal engineering, molecular engineering. We looked at chemistry that can be done with undergrads, okay, and regular characterization with focus on two tools. Actually, this tool that chemists use regularly is called cyclic voltammetry. It's an amazing, simple tool, but it tells you how easy it is to add or remove electrons from any molecule as you sweep potential. And then we became also interested in X-ray diffraction, whether single crystal or powder diffraction. Of course, ideally, we'd like to get crystal structures to see exactly how the molecules pack. And we ran into a lot of different polymorphs. And the problem is, I think this still needs warrants more studies. If you have two polymorphs of an organic semiconductor and you put them in a device, we were not able to do single crystal devices, mostly thin films. It would be interesting to have a cause-effect relationship between packing and let's say mobility. We looked at polymers versus oligomers. We chose to stick with oligomers, small molecules. At least we know exactly what we have. And as I said, these experiments were done by undergraduates. And in fact, we developed experiments that those of you who teach organic chemistry labs or physical chemistry labs or analytical chemistry labs, instrumental analysis lab courses, some of these guys are amazing in teaching these techniques. So we developed some experiments. In fact, one is being evaluated at the Journal of Chemical Education right now. So again, the chemistry is rather few reactions to master, telecoupling and Knoevenagel reaction, bromination reaction with TCNE, and Bilsmeyer reaction and Vidic reactions to make the polyenes. Again, this is our lead compound. We published that in 2003. And then since then, we have tried to work with thiophene, E-dot, and tricyanovinyl group, and later on the dicyanovinyl group, as we shall see. This is what I was mentioning earlier. We made a series of molecules. You can see that we increased the number of thiophene units from 3 to 4 to 6. And we put cyano groups on both sides. And we ran cyclic voltammetry experiment. So cyclic voltammetry, you start from zero potential, you sweep in the negative. That means you are adding electron, you add the first electron, you add the second electron, and these are reversible. You can remove them back, and then you go back in the other direction. Okay, and then now you oxidize the molecule. Physicists refer to this as polarons, bipolarons, all. We refer to this anion, dianion, cation. Okay. Now, when you increase the number of rings in the middle, you have more electrons to remove. So instead of one peak, you see two peaks. And this molecule, you can oxidize, you can add electrons easier because the cyano, 6 cyano groups, each one of them can take 1 electron. So you can, in theory, you can put up to 6 electrons. But of course, the dielectric constant of the solvent does not allow us to do so. So we assume the solid state, maybe it would you would be able to add up to 6 electrons, depending on how the molecule is packed. So we can add and remove electrons, and indeed we did this work in with Dan Frisby's group, and we showed unbipolar behavior. This molecule here, it shows both N-type and P-type semiconducting. So it conducts both negative charges and positive charges. It's not symmetrical, but that also another area that probably needs more study. Can you achieve symmetrical conduction if you increase, let's say, the number of rings, but the synthesis becomes a little bit difficult. Just to give you an idea, sometimes common sense, we all, when we teach courses in general chemistry or undergrad or grad, we try to teach common sense. And sometimes common sense really is beautiful to look at. There was, in Dan Frisby's group, they came up with this, that a Tollel group really produces beautiful thin films. I mean, it's good on substrates. It makes good films, good thin films. And we learned from the crystal structure of thiophene with tricyanovinyl that they form pi stacking. So we said, okay, what if we put both in one molecule? So it would both form pi stacks in a good thin film. So we went after molecules like that, where you have the Tollel group to form good thin films and the cyano groups to induce pi stacking. Neither one of them happened, unfortunately, but sometimes, you know, things are great on paper, but in real life in lab, they kind of lag behind. Again, I will just quickly go through some of the structures. Hopefully it's not boring for those of you who are not interested in packing or solid state structures. We look at this molecule here, and we know it forms pi stacks with about 3.2 angstroms between the molecules, like stair, like a ladder, literally. If we introduce a double bond to increase the conjugation, we form what we call a dihedral angle now, or a torsion between. And then we introduce these butyl groups, 4 groups, to enhance solubility for film formation from solution. Again, so every time you modify this, this and the long groups create spacing that is undesirable. The synthesis for anyone is interested. So we became interested. How about dicyano instead of tricyanovinyl? Let's take a look at, instead of 3 cyano groups, we have 2, and we use what we call Knoevenagel condensation. Very simple. So you start with the aldehyde and you react it with malonitrile, basically. Malonitrile being CH2CN2. And again, we solve the crystal structure for these molecules. As you can see, you can form pi stacks here, and you can add and remove electrons rather reversibly. One molecule here, this molecule is really unique. I think it's fascinating to me. It's such a small molecule. It forms sort of a DNA kind of helix structure, polar crystal structure. And that would be very interesting for people, again, who are interested in solid state packing. Now, I switch gears to talk a little bit about the triphenylamines before I conclude. We looked at triphenylamines, the same thing. We developed this chemistry, actually. You can do it at room temperature, literally. Before that, people used to use N-butyl lithium, and that's extremely dangerous and stuff like that. So it forms, basically, you mix the 2 materials, tetracyanoethylene with DMF for 1 hour. It forms deep, beautiful purple color. When you crystallize it, you get these shiny green metallic crystals. And this is the UV visible absorption. This is the crystal packing. It forms sort of a fan or sort of a propeller shape packing. And now I looked at just to give you what does crystal structure tell us. You can actually view the conjugation length. How is charge transferred? There is a significant shortening of the length along the, this is 1.38, for instance, 1.36, 0.45. So you can actually guess what is the conjugation length in these molecules. So there is intramolecular charge transfer in all of these molecules, and probably that is why they have this metallic shiny structure. We looked at a variety of triphenylamines. We didn't publish this work yet. We looked at the brominated, tricyanovinyl, dicyanovinyl, tricyanovinyl with the methyl group, and we looked at how they pack and all that stuff. But I will go through this. If anyone is interested, please let me know. You can either send me an email or in the chat. I will follow up with you. We looked at the DFT calculations to get a better idea. These are calculations carried out on gas phase molecules, isolated gas phase molecules. It gives you at least an idea of the homo-LOMO. So if you start with triphenylamine, this is the LOMO and this is the HOMO, upon putting a DCV or TCV, the most significant thing you see is that the dropping of the LOMO level resulting in a lower band gap. So later on, we became interested in raising the HOMO level and dropping the LOMO level in the molecules that we synthesize. Now, intermolecular forces, we became interested in the role of halogenation or bromine atoms on optical and on the electrical properties and solid state structure. If you look at these two molecules, these are E dot molecules. One is brominated. This orange here is bromination, and one is not. The dimers in the solid state go from nitrogen-sulfur interactions, and now the bromine-nitrogen interaction supersedes the nitrogen-sulfur, so you get a larger cavity or a different form of dimers. And but these holes, if you look at this stacking in this direction, you are looking at a tunnel. I don't know what to do with these tunnels, but probably there might be some applications for that. We looked at the two E dot units with bromination. They form different patterns. We looked at, for instance, terthiophene, 3 thiophene units. And again, we learn as we go, but the take-home message is literally bromine does play a major role in interacting between either bromine-bromine interaction like here or bromine-nitrogen interaction, in addition to bromine-bromine interaction with a twist. This becomes now, instead of stack, it becomes like of a tilted packing. Now, the optical properties, very quickly, I'll just, the take-home message here is that you can see that we looked at triphenylamine with TCV group, tricyanovinyl group, and then with bromination. Both, the most significant finding, I guess, in this is the solvatochromic shift. It goes from plus 14 nanometers to minus 14 negative. These are fascinating. And again, the same thing with the emission and the optical studies, probably they call it heavy atom effect. Again, the same thing we see in brominated thiophenes. What we saw in the triphenylamine and the brominated triphenylamine, the same thing, it affects the emission. This is S10 here. Without bromo, the emission is 644, 626 with the brominated.
Sorry to interrupt. We have only 1 minute left.
Okay, I will conclude. Thank you. All right, this is basically the conclusion. The conclusion is that controlling molecular structure in terms of synthesis versus controlling solid state assembly, we are still learning. We can make molecules, but we can't tell them how to crystallize or how to pack in the solid state. There are many variables that, but it's an interesting field. I'm sure for all devices, the packing, whether in thin film configuration or in single crystal devices, the way molecules or units, it could be nanoparticles, could be anything, would play a major role. So I think scientists need to look closer at this packing of molecules and how does that impact charge transfer. growth onto surfaces versus bulk. We looked at the functionalization of surfaces. Let's take this molecule and grow crystals on glass versus gold, or versus, let's say, self-assembled monolayers, and so on. Polymorphs, again, this is an interesting field. Undergraduates can do a lot of work with that, and they get excited, especially if you give them pharmaceuticals. We work with, like, even ibuprofen, for instance. We think we have 2 different crystal structures for the 2 enantiomers. This is being looked at the University of Minnesota right now. Finally, I'd like to acknowledge my collaborators over the year, Professor Mike Ward at University of Minnesota, who's now at NYU, Dan Frisbee, Victor Young, Director of X-ray Lab at University of Minnesota, Wenfang San at North Dakota State University, who did where we did the optical characterization. Charlie Spangler at Montana State University. Research grants from Al Faisal University and the Penn State University, and Mersic, both at University of Minnesota and NYU, and Boeing research grant at Al Faisal University. My students who worked with me over the years: Lamia, Al-Fahid, Tarfa, Rawaf, Munira, Suwalim, Filwa Hussein, Dima, Al-Midami, Ghada, Uthman, Justin Moser, Leslie Albright, Greg Gottschall, Whelan, Anelio DiMarco, John Machiski, Joe Scheller, Bill Fillin, Tayala Carvalho, G. King, Chen, and Basant Nassar, Kyle Picht, and Eric Picota. Thank you so much.
Professor Bader, thank you for your impressive talk. If anyone has question, please type your question in the chatting region.
Yes, I have a question.
Sorry, we do not have time for question. If you have any question, please type it in the chatting region.
Okay.
Sorry for that.
I'm looking at the chat.
Okay. Professor Bader,
okay.
Would you mind stop sharing?
Yeah, sure.
Thank you. Our next speaker is the Professor Zhen Haimei from the Lawrence Berkeley National Lab.
See my screen?
Yeah, perfect. Could you hear me? The screen looks so perfect. Looks good.
The study of electrode-electrolyte interface facial phenomena using liquid phase electron microscopy. The liquid cell electron microscopy has advanced significantly in recent years. It has enabled many exciting topics of study. It can direct image the dynamic reactions and individual events in liquids with high resolution. And so it is complementary to the X-ray ensemble techniques and scanning probe microscopy. But it also has a number of challenges. It also has a number of challenges. For example, the microscope has very small Popey's gap, which requires the sample cell very small, and their electron beam damage and better control of the reactions. This is especially true for study electrode-electrolyte interfaces. In the past, in my group, we developed liquid cells, and there are 2 types of liquid cells we have been developed. One of is regular liquid cells without the electrode. This we studied a lot of many different systems, and with a focus on getting higher spatial resolution. to really show atomic resolution, the dynamic processes occurring in the liquid. For study of the electrode-electrolyte interfaces, we develop electrochemical liquid cells. And for this development, we also had a variety of electrochemical cells with different electrode design. And later, I would show you a few examples that we use the electrochemical cell to study the electrode-electrolyte interfacial phenomena. And for this part, we are not really pushing the resolution because I said the electron beam damage is a concern. We try to really see that what we can do the best using this cell to get information that avoid the electron beam damage. Here is showing the earlier study of the deposition of lead, as you see the dendrite formation, and we make sure before we apply electric bias, and there's no deposition, no changes in the electrolyte. So this is purely due to the electric biasing. After reversing the bias, we can see the dissolution of the dendrite, and we can also look at lithium deposition, SEI formation, and we can also look at if we create electrode with surface roughness and how the deposition behavior changes. And in this talk, I would like to show you the very recent study on the lithium deposition behavior changes by applying a polymer film on the electrode. We coat the electrode with PTDA polymer film. Then we try to study this polymer film impact on this deposition. I just wanted to mention that this electrochemical cell, the liquid cell we're mentioning, we just use very thin, very small amount of liquid in the nanoliter range. So in order to deposit this polymer film is a significant effort. We try to use very thin, as you see, or when we do the spin coating of the polymer film inside the clean room. Well, normally we have the micron thick polymer. For this liquid cell, and we only have 100 nanometer gap. And then here, we deposit the PTDA film using nanocrystal as a carrier. And so we can load very thin amounts of the PTDA to coat electrode. And this movie on the left showing with the polymer coating and the lithium deposition shows very interesting nanogranular growth. And this is the snapshot image from this movie. And this is drastically different from the deposition behavior without the polymer film. On the right side, we can see the lithium dendrite formation on the bare electrode. And this large lithium deposition formed on this electrode. As you see here, continue growing, this lithium deposition very large and different from this on the left side, the nanogranular growth. And we try to figure out the mechanisms behind. And for our liquid cells, we try to make it thinner and thinner mostly, and this electrochemical cell allow us to do EDS chemical analysis, which is very hard to achieve compared to the commercial cells or other thicker cells. The silicon back etching actually block the signal, and we use ultra thin silicon wafer to made this electrochemical cell, so we can do chemical analysis. And it shows, and this detailed structure, fine structure of SEI with this different elemental mapping, we can see that the lithium fluoride rich inner layer within the SEI, which is a major difference compared to the one without the polymer film. And we also did control experiment. And this is the, we did the, from a battery cell, and then we get collected the samples and XPS analysis. Of course, this is an ensemble study, and we can see without the polymer film, we have large grains, and with the polymer film, we have nanogranular growth. And very interesting here is that we do see the lithium fluoride rich layer coming out from the polymer coated electrolyte, polymer coated the cell, and this consistent what we observed in our liquid cell in situ experiment. And so this is very interesting. It shows that with the polymer coating, this same electrolyte with one millimole of the commercial electrolyte for lithium-ion batteries, without increasing the fluorine concentration, we can actually get reach higher concentration of lithium fluoride within the SEI to improve the SEI quality of the individual grain, and that preventing the dendrite formation. That in situ study allow us to identify the mechanisms, and this we can not only to study this deposition behavior, but also we can look at the stripping behavior of the lithium deposit. And we can focus on the origin of the dead lithium formation and the role of SEI in the lithium stripping. This again will compare this nanogranular morphology of the lithium and as well as the dendrite, lithium dendrite. And this is a movie showing that the stripping of the nanogranular deposit of the lithium. And we can see there are a number of interesting behavior of the lithium stripping. And this arrow shows the grains of the nanograins of the lithium, and some of the lithium, most of the lithium deposits disappear during this process. We can also see a few newly deposited nanograins. The interesting part, the first is we found the lithium are stripped not simultaneously, and we see it's quite irregular, and that is surprising. We also found this different dissolution behavior, and it's summarized over here, symmetric and asymmetric. And this asymmetric dissolution of the lithium nanograins mostly related to the defects within the SEI, and the thinner, the interfacial preferred dissolution, mostly we consider the thinner SEI at these interfaces. This gave us important clue about the dead lithium formation in the lithium stripping process. And this behavior is consistent with the stripping of the lithium dendrite. And of course, with this here, dendrite are forming this joint between these different big grains of the dendrite. It also shows the interfacial preferred dissolution that contributes to the dead lithium formation. And assuming each of the grain dissolution of this lithium is the point source for the lithium ion diffusion. Using this equation, we can calculate the ion distribution of the lithium. This is important information. It shows that consistent with our previous the observation that the not irregular dissolution, mostly because of this the increased local concentration of the lithium ions, slow down the adjacent neighbor of the dissolution of the lithium. It goes facilitating the stripping of lithium somewhere else. And the next question is whether this good SEI can be beneficial for the next cycle of this stripping and its dissolution. And from here, we did careful analysis again. And conclusion here is that we also found the significant changes of the fluorine concentration in this dead lithium, this lithium going away. And the conclusion here is that actually the good SEI formed in the previous cycle deposition is not so beneficial for the next cycle of the stripping. It actually still have a lot of this dead lithium because of the interfacial stripping of the lithium. So there are a lot of interesting phenomena that can only be resolved for the in situ observation. And I would like to acknowledge and the work mostly done by my previous postdoc, Seung Lee, for the later two work. And he is become a professor at Hanyang University in Korea, and liquid cell fabrication from my graduate student postdocs and collaborators. Thank you for your attention. I would be happy to take any questions.
Professor Zheng, thanks for your excellent talk. Since we do not have too much time, if you have any question, please type your question in the chat. Thanks for the talk again. Professor Zheng, would you mind stop sharing? Our next speaker is Professor Marguzeta from the Adam University. Professor Marguzeta could not join us today, but she recorded a video for this talk. Jingyuan, could you please play the video? Sorry, I could not hear it.
Can anybody see the screen?
I can see the screen, but I cannot hear it.
Okay. Sorry, I will change the. I was setting it. Is it okay now?
Still no voice.
We can hear now.
Oh, okay. Maybe it's my bad internet.
You are. Can you hear?
Yes.
Oh,
Sorry. Can you hear the voice?
I could not. Is there anybody can hear the
I
voice?
can hear.
But we could not see
We
your
can
screen.
hear, but we can't see the screen sharing.
You cannot see the screen?
That's right. We can't hear. We can hear you now, but do not see the screen, your slides.
Can you hear and see the screen now?
Can hear, but we can see you, but not.
We cannot see her.
Can you see the video now?
We can see the video, but no sound.
No sounds. Okay. 把这个声音打开。
For the conference. We would like to present our results and try the phase transition of MTTC ionic liquids confined in nanocarbons.
Can you hear the sound?
Yeah.
Okay, let's start from the beginning.
I would like to thank very much the organizer for invitation for the conference. We would like to present our results and try the phase transition of MTTC ionic liquids confined in nanocarbons. The confinement effect has a many applications in many fields. The porous matrices like mutual carbon nanotube, hierarchical carbon, CMK3, confinement effect is recently very much studied with application in microelectronic, gas sensing, environmental protection, energy storage, gas separation, solar cell, and in medicine. Our aim was to understand the base behavior of ionic liquids within carbon nanopores. As the ionic liquids, we use MTFC, consists of the cation and anion, and also microporous carbon, which have the cylindrical pores with the pore size about 1 nanometer. Currently, much research in electrochemistry is concerned with the effect of direct application of the ionic liquids as electrolyte or supercapacitor. Ionic liquid consists entirely of ions as they operate as solvent-free electrolytes, exhibiting significantly higher operational voltage than classical organic electrolytes. Due to the fact the operation condition for supercapacitor require low temperature, an important issue is an investigation of melting behavior of ionic liquids applied as an electrolyte. As it is known from the literature, the melting freezing behavior in porous media can show increase of the melting temperature of the substances, confinement substances relatively to the bulk, and also decrease of the melting temperature of the confinement system relatively to the bulk. It is the criterion of the increase or decrease melting temperature so far is the alpha parameter, which is the ratio of the fluid wall to fluid-fluid interaction. If this parameter has a high value, we can expect increase of the melting temperature, and for the lower value of alpha, we can observe decrease of melting temperature relatively to the peak. As an experimental method, we applied dielectric spectroscopy, differential scanning calorimetry, in wide temperature range, and also structural properties we investigate using wax and photon diffraction method. Such an experiments were done for MTTC bath and MTTC placed in porous nanocarbons. Results of the differential scanning calorimetry and dielectric spectroscopy show that melting behavior of the ionic liquids is not homogeneous. We can, at lower temperature of the DSC scan, we can distinguish endothermic peak at temperature about 270 and also peak related with the heat release due to the venting process. So we can see that we observe solid-solid transition for the ionic liquids below melting points. The same results we can see from measurement of dielectric capacity versus temperature. So we can see the change of capacity at the temperature typical for the solid phase transition and big change of the capacity typical for the melting behavior as the dielectric as the orientation and polarization of the molecules is not exist at the solid state. So we can see big increase of the capacity at the melting point. We measure complex permittivity versus frequency. So we were able to, using the Debye dispersion relation, to estimate the dielectric relaxation time, which describes the molecular motion in the solid of any molecule. At the solid state of ionic liquid, we find few kinds of the molecular motion, which are stable at temperature range until about 230. Then they change and they vanish above the melting point of the ionic liquids. It is interesting feature because on the basis of the structural method, we find that at lower temperature, we have a stable structure of the solid state. Then at temperature about 245, the structure is changed, and also from this point we observe the change of the relaxation motion. It is the temperature 245 is the temperature above the solid phase transition. We find that at the lowest temperature, the ionic liquid has a monoclinic symmetry. Symmetry for higher temperature was undefined for us. The similar results we had from neutron diffraction experiment. We can see the stable structure of solid ionic liquids until about 240, and it has changed at the temperature higher than the solid phase transition. The results for confined ionic liquids show that we can, the results of DSC show the typical peak of the melting temperature of the bulk system, as we have an excess of the system, or in the system of the bulk substances. And the additional peak is related with the pore melting point. It is divided for the two Gauss curves, showing that the system is not homogeneous and the peak is not regular, the peak showing the pore melting point. For lower temperature, we can see solid phase transition typical for the bulk liquids. Similar results we can see from measurements of dielectric capacity. We can see 2 points of change of the capacity related with the melting impulse, and big change of the capacity related with the melting of the bulk substances. Analysis of the dielectric relaxation time show that we can see here additional branch of the relaxation time. The great point, the relaxation time related with the bulk behavior of the bulk substances, but we can see additional branch which is changed at pore melting points, and it is slower than the melting point, the relaxation time typical for the bulk substances. This relaxation time can be related with the relaxation time is related with the substances confined in pores, and it has a different value because of the interaction pore walls with atomic with ionic liquid molecules. Analysis of the structural methods for confinement systems show that we can see a solid structure at lower temperature, which is not changed until 240. At higher temperature, we can see the change of the structure of the system related with the solid-solid phase transition on the bulk and also with the pore melting points. The same results we can see from neutron diffraction results at lower temperature until practically 240 is no change of the structure of the system, and changes we observe at since 250 Kelvin, where we have a solid-solid phase transition and also a melting point in pores. As a conclusion, we could say that the melting process of any 33 is not homogeneous. The ionic liquid on the heating process undergoes to phase transition, solid-solid transition at temperature 240 and the melting transition at 258. In the temperature range 10 to 240, chemical FESC forms a crystal monoclinic structure where the rotation motion of molecular groups are observed. At the higher temperature, up to the melting temperature, the crystal structure was undefined and the rotational motion of molecular groups was changed. The melting temperature of amine confined in nanoscarbons pore decrease relatively to the bulk and is about 253 Kelvin. We observed in pores, similarly as for ionic liquid bulk, the existence of the rotational motion of ionic liquid molecular group below melting point, which is slower than this motion for ionic liquid bulk. It can be the result of the ionic liquid pore walls interaction in confinement system. We conclude also that any FESC with a melting point at sub-zero temperature can be a good choice for the application as an organic electrolyte in supercapacitor operating at low temperature. I would like to acknowledge the group of Professor Gaddings from North Carolina State University, and also to my team from Poznan, Poland. Thank you very much for the attention.
Okay.
Okay. Thanks, Professor Magrizetter's video. If you have any question, please probably you need to contact Professor Magrizetter via email. Our next speaker is Professor Wei Xianhui from the Research Center Zurich. Professor Wei has a bad internet, so we still need to play his video. Jingyuan, could you please play Xianhui's video?
Good afternoon, everyone. My name is Xianhui Wei from Research Center Zurich. Firstly, I'd like to thank the organizers for giving me this chance of sharing the results here. So today, I'm going to give a talk about self-epitaxial heterogonal layers and the real space topological ferroelectricity discovered in nickel phosphide. Nowadays, clean and renewable energies are highly demanded because of the limited reserves of fossil fuels. Water splitting through electrolysis provides us an effective solution to produce hydrogen energy. Nevertheless, the noble metals are also limited in reserve. To realize sustainable energy production, substitution of noble metals by cheap and efficient catalysts are highly demanded, and the transition metal phosphide is one of the candidates for this purpose. It has been reported that nickel 5P4 and the nickel 2P1 are highly efficient catalysts in hydrogen production. Specifically, the 5,4 phase has been reported to possess platinum level activity in sulfuric acid. Nevertheless, more results show that its activity is comparable to that of the 2,1 phase. So this rose our curiosity to explore its surface structure. The DFT calculations on these two phases show that their 1 surfaces are highly efficient in hydrogen evolution. And here we see that their surfaces can be reconstructed in a very complex way. To explore their structure and property relationship, we therefore carry out a atomic-scale TM study on the nickel phosphide system. So here, in this talk, I will show you two findings. One is core shell structure feature identified in the 5,4 phase of the nanosheets. And the other one is discovery of topological ferroelectricity in the nickel 2P1 system. Regarding the nickel 5P4 nanosheets, our electron diffraction experiments reveal that they have preferential delta-1 orientation. And this is the higher solution TM image recorded along the 1 direction. From the image with filtered intensity, we clearly see the atomic terraces, which evidence the surface reconstruction. And this is further evidenced by the intensity profiles of atoms within the blue hexagon. Interestingly, our electron beam bombardment experiments reveal presence of a thin layer of 2,1 phase on top of the 5,4 phase. So this is consistent with our nickel-rich EX result and the structure model shown on the right-hand side. For simplicity, we carry out further structure study using HardStem. Through image simulations, we found that the ideal 5,4 phase cannot interpret our experimental results. So this can be found by comparing these two images. Instead, only one proper vacancies are considered at the nickel sites. The surface reconstruction can be reproduced. So here we show comparison of the simulated image with the experimental one, where a thin layer of nickel PX, nickel 2P1 nanolayers are overlapped on the 5,4 phase, where the thickness is about 2 nanometers. So from this specific atomic size, we can clearly see the reconstruction is well reproduced, although our structure solution is not unique. Our measurement showed that the heterogonal layers leads to passivation of the 5,4 phase. The valence state of nickel and phosphorus in the bulk form arose our curiosity because of their seemingly ambiguous solution according to the electroneutral law. Apart from this, the coexistence of metallicity with structural asymmetry also arose our curiosity, since in ferroelectric insulators, these two physical quantities conflict with each other. So here, to find out more details, we focus our attention on the nickel 2p1 phase. The phase purity is identified by SRD, EDX, and the Hardif stem about the nanoparticles. Our previous study on ferroelectricity revealed that to charge the means with unequal polarization will lead to unstable structures at the domain wall center, which is manifest by presence of the in-plane polarization component. So the same thing should apply to the nickel phosphide system, which have polar pyramids and the tetrahedral. On this basis, we construct a series of symmetry equations about polarity, where the atomic size of a nickel 1, nickel 2, and their valence states are taken as variables. So associated with the electroneutral law, we find the analytic solutions. So we see the valence state of nickel and the phosphorus have intimate relationship, and also the polyhedral polarity linearly coupled with the valence state of nickel and phosphorus. For two experimental data sets about the crystal structure for nickel 2p1, we found the polarity configuration may change from center divergent to center convergent, and both of which have a Wannier number of 1. To verify the analytic solutions, we measure the valence state of nickel using EVIS. Referring to the nickel standard, our measurement using white line intensity method revealed that nickel has an average valence state of 0.5. So regarding nickel 1 and nickel 2, which locate at the center of the tetrahedral and the pyramids, the valence state is 0.4 and 0.6 at the atomic resolution. By combining by exploring the bonding energy and the valence state relationship in a series of phosphorus containing compounds, we find out the valence state of the phosphorus in the compound is about -1 through use study. Specifically, if considering all possible 3D 4s electron occupancy configurations and the charge relation about phosphorus, each of the element has an effective valence range, which are shown here. And these results will agree with solution from our symmetry equations. So regarding the topological polarity transition, our DFT calculations reveal that an in-plane compressive strain may lead to this transition. Meanwhile, we found presence of a tunable bilayer double well potential while applying the compressive strain. To further verify the topological polarization, the rush-bar effect was examined by considering the spin-opto interaction. Due to absence of a structural invariant symmetry, spin degeneracy is lifted in our calculation, and we found that the spin polarization coupled with the polyhedral polarity, which is manifested by energy state at -0.8 eV near the zone boundary region. Furthermore, our DFT calculations also show this nickel 2p1 phase show metallic state before and after the compression. So now in this system, we see that many physical quantities couple with each other: the switchable polyhedral polarity, topological feature, valence state, spin polarization, and so on. To describe this intimate coupling between so many parameters, we therefore coin a new term, that is topological ferroelectric metal, which should represent a new class of materials. This finding points out that we may explore new interactions between topological ferroelectricity with ferromagnetism and the superconductivity in asymmetric compounds. And also it presents a spin level understanding to the electrochemical reactions in energy conversion materials. So with this, I would like to make a summary. In our study on liquefied P4, we found presence of self-epitaxial heterodyne layers, which leads to passivated catalytic activity. In the nickel 2p1 system, we establish a new material system, which is called as topological ferroelectric metal. So this finding expands the research scope of ferroelectric physics to topology. Meanwhile, it presented new insight to understand the catalytic reactions in energy conversion materials. So at the end, I would like to thank my colleagues and also funding from the EU about our recap project. Thank you for your attention.
Thanks, Professor Xiankui's video. Our next speaker is Professor Xingbong Hong from the CARES. Professor Xingbong, could you start sharing?
Yes, please. Just a moment, please.
Mm-hmm.
Let's see if it works. Okay.
Yeah, it looks fine.
All right. Thank you very much, Chairman. I'd like to thank all of the organizers to give me a chance to present our research on M3I3. This is Materials and Molecular Modeling, Imaging and Informatics and Integration. And this is part of the Global Singularity Project at KAIST. So this is the picture where you can see some of the members of our M3I3 project, and you can also find it in the website shown below. And I thank all the members here. And the most of the contents that I will cover today is published through ACS Nano this month. And for interested readers or audience, please pay attention to this paper. First of all, I'd like to revisit the question how we divide our history into important segments. And this is all known to even to my kids, that the materials that human beings used are the way we name our era, and that represents the impact of new materials to human society. But at the same time, you will see the time that we needed to develop new materials. For example, if you start from stone to bronze, it took like 2,000 years. So there is obviously an impetus to accelerate the materials discovery in a way that can impact our society. So how do we accelerate the materials discovery? This has been the buzzwords for like 20 years in the world, and we are not the only one to think about it. But we have come up with this picture where on the left side, you can see the hierarchical structural relationship starting from atomic structure, linking to bulk structure, and see how the multi-scale and complicated relationship between structure and property, as well as the processing structure, can be facilitated not only by the machine learning and AI, but also by the materials imaging capabilities that are available today. So I'm starting with one anecdote from Korean history, where a person named Jang-ho Kim became an AFM probe himself to scan the Korean peninsula 9 times over his lifetime, and came up with the accurate landscape of peninsula and locate the highest mountain, which was Mount Baekdu. But nowadays we can use GPS satellite image to get the picture more accurately and in a shorter period of time, and also cover the whole globe instead of just Korean Peninsula. So now we are at a position to get the global maximum rather than local maximum. So what does this mean? This means that we can think about the imaging capabilities from 16th century, where we use optical microscope to see the shape and structure. Obviously, this helps us to understand for example, martensitic steel, why it's so strong in terms of the structural features. And obviously, microscopes have been very important up to now. However, if we think about the question here, what breakthrough in materials imaging created a paradigm shift, it is not sufficient to say we can visualize the shape and structure of materials, and so that we can come up with a better property. So the question here that links with the materials discovery is really structure and property imaging at the same time. So one other example in Korea, because we use neighbor maps, is that not only we know that, for example, the distance between Daejeon, where I'm living now, and Seoul, but also we know the traffic situation, which will be the property of this traffic, so we can get the accurate travel time. It's not just dividing the distance by the average velocity, but it's also considering the traffic situation, so we can see the dependence of travel time as a function of different parameters. Moving to materials world, we can do the same thing. For example, in battery materials, this is some examples from our group where we were able to visualize the topography of composite electrodes. At the same time, we were able to see the lithium-ion distribution and also the friction coefficient, which could be the marker for the components like binder and active materials, so that we can plot the correlation between, for example, the lithium-ion diffusivity and the components like natural graphite, LSTP, which is solid-state electrolyte, and binders, something like PVDF. And also going further, we can also calibrate the lithium-ion diffusion coefficient using other chemical tools and correlate at the multi-scale that is shown in this slide. So what does it mean? We can now understand or estimate the accurate charging time based on those images. Structure property imaging is not only limited to battery materials, functional materials, something like ferroelectric materials that were presented by the prior speaker. We can now not only see the topography, but also the dipole moment, as well as the screening charge on top of it, using different markers like the screening charge on top of it, or the channel resistance between source and drain that is embedded in the AFM tip. So this is another example to have structure property imaging. And another anecdote I would like to bring to your attention is, like, what if in addition to the landscape we shown in the Korean Peninsula, if we have the quantitative information of cost and benefit in terms of money and environmental impact, and we are to, say, construct a canal to connect west and east. And if we can make that decision based on that imaging map, then that will be very fast. Similar things in material science is the mesoscale canal that we made in zinc oxide. So zinc oxide is a brittle ceramics, but by having these canal, we are improving the elastic limits. So we could use this for example, haptic enhanced materials, where we have the piezoelectric constant intact, but the elastic limit improved by, for example, 10 times than bulk ceramics. So now I'd like to switch the gears to think about what is the trend about the materials by design, which was a buzzword in the early 21st century. The pioneers were in the UC Berkeley and Lawrence Berkeley lab. You can find this materials project. Oh, sorry. And one example here, you can see based on DFT, you can visualize the atomic structure as well as the band structure at the same time. So you can correlate the structure property relationship at this scale. Not only that, you can also estimate other materials properties. And now they have hundreds and hundreds of thousands data sets that are stored in their cloud, which are accessible to anyone who are interested in this website. Now, DFT is costly in terms of computing power as well as the way that it is calculated. So based on the particular exchange functional, it could be inaccurate due to the cost considered. And in addition, the predictions are all based on calculations, so should be validated by experience, which could be timely. And as such, the data quality has been always the centerpiece of the discussion when we wanted to use machine learning. Not only that, there are some political consideration where some of the competitors do not want to reveal all of the experimental data set, so that this is being a current challenge. Now, this boils down to the problem of small data set with high quality. And one way we are thinking is to tackle the user facilities around the world, because they are creating tons of experimental data sets, especially in by using materials imaging by X-ray probe, for example, Raman or STM, and TEM and AFM, and also utilizing the policy of open and transparent data publication, so we can tap into that vast data sets. One of the user facilities I was involved was Argonne National Lab, as you can see in this page. And this is just one example we can use. And using that Argonne National Laboratory user facility, I was able to, for example, tap into the functional property correlation between the conductivity and the structural information like magnetic phase formation in a form of filaments. So you can see that using user facility, we can have similar sets of data that could have some information about structure property correlation at multi-scale. Another example here is again from Argonne National Lab, where we use Raman imaging and GSOX and GWOX to correlate the conformation within the PVDF polymer ferroelectrics and the appearance of new phase, as well as the long-range ordering in these polymers that resulted in property enhancement. So these are two examples that I wanted to show that indeed user facilities are some of the good sources to enhance the small data set problem of the materials discovery. In Korea at KAIST, we started this M3I3 around 2018, and now you can see in our website that we are very serious about this with the long-term vision. So if you're interested, you could visit this website, which is written in English. And one example that we tackled was this battery materials, especially cathode materials that has been developed for like 30 years. The NCM started with the Sony Vaio laptop battery, now has moved to nickel-rich composition. And we wanted to see if we can revisit that development process and see if at that time machine learning were available, whether we could accelerate that process. So on the top part is the conventional way to correlate the property, structure, and processing using machine learning, and then reverse engineer the recipe. The bottom part is ignoring that and dumping all of the texts that are available in the website using unsupervised learning, and see if the machine can extract the feature parameters that are important for high density cathode materials. So this is the plot you can see from composition of lithium cobalt to lithium mangan and lithium nickel oxide materials, where it started from pure cobalt going through 333, and then now moving on to nickel rich that are correlated with energy density. And we did this kind of mining using our members of the project and did this curation. And you can see there are a lot of empty spaces, which were now later filled with machine learning tools. And then we filled that out and made a quantitative models to reverse engineer the well-known materials and validated by experiments, as you can see in the table. And that was about 10% error. So now revisiting this process and seeing that we can accelerate that, we're now moving to this future candidate materials where we have less data sets, and see if we can use the transfer learning or augmented methods to accelerate the future materials discovery in cathode materials. The other way around that I showed you was to use the multi-scale libraries between property and structure and processing, and that are based on some of the technologies that are available in the world, like atom probe tomography. APT obviously can show you the distribution of each component and see how in and out of lithium will change that structure and how that influences the charging time and the energy density at that scale. Another interesting way to show that is through 3D STM EDS tomography. This was on the NCM 523 samples, and plot all of the elements in space, and this could give us the basic baseline for the atomic structure property relationship. And then moving on to nanoscale and microscale, we can use AFM and X-ray as well as macroscopic property measurements tools to see how, as a function of state of charge, the lithium distribution as well as the crystalline lattice parameters change and correlates each other with the, for example, energy density at bulk scale. So with that, we are now moving on to electrolytes as well as the membrane to cover the full system of battery materials. And once we are finished with that, we think this algorithm is not just specific to battery materials, but other classes of materials like memory materials or even food and cosmetic molecules. So that's the vision that we currently have, and that's what we are now working on. I'd like to thank the funding agency, mainly the KAIST internal block funding, and I thank you for your attention. Thank you.
Professor Seung-Woo Hong, thank you for your interesting and impressive talk. If anyone has any questions, please type your question in the chat. Our next speaker is Professor Adam Weber from the Lawrence Berkeley National Lab. Professor Hong, could you please just turn off your sharing?
Yep, thank you.
Professor Adam, you can start your sharing.
Great. So I assume you can see the slides okay and hear me. Thanks for the introduction. And today I'm going to talk about the structure from darkness. So really looking here at fuel cell materials and fuel cell performance, starting from kind of what goes on within those porous electrodes. And so this was primarily work that was done by two graduate students who just graduated, Sarah Berlinger and Namika Chowdhury. So when we talk fuel cell catalyst layers, these are very complex porous structures, like most porous electrodes, to where we have gas pathways and porosities to get our reactants in. We have these ion conducting polymers or ionomers, which coat these catalyst surfaces. And so here you can see they partially coat them, not necessarily fully coat them. And that's on the order of nanometers. These agglomerates on the orders of tens of nanometers. The whole system's on the orders of microns. And so understanding the structure becomes very complex and trying to understand what the overall implications are for performance. So for example, one of the things we want to do is increase the amount or decrease the amount of catalyst because of cost considerations. But what we see is when we decrease that, we get a strong increase in the overall resistance for performance. And so this is tracking by saying something very local is limiting, because when we decrease the loading, our flux to the individual sites is increasing. And so if we have a resistive component, it's going to increase exponentially. And so how do these catalyst layers get formed? Really what we want to do is link what goes on at kind of the ink level to the actual catalyst layer structure and then its performance. And to do that is a lot of properties and a lot of different processing that we can consider. And so the simpler way to do is take a subset and look just at some of these individual interactions, which is what I'll talk about today, between the ionomers, between the solvents, and between the catalyst particles. And so to do that, we have a matrix like this, where we're changing the equivalent weight of the ionomer itself. We can think of this as just kind of the inverse of the ion exchange capacity, or essentially the amount of spacing between these ionic groups. These ionic groups are typically sulfonic acids, and so they're hydrophilic. The backbone of the polymer is hydrophobic, and so we get some phase separation. And so we want to look at the water content in the solvent, as well as different substrates. So going from hydrophilic to hydrophobic substrates to help deconvolute the different interactions. And so we've done this with different methods. So shown here on the left is a quartz crystal microbalance, where here we're looking at the change in mass, so the uptake on a different substrate of the ionomer itself. And so what we see is when we're going towards a more hydrophilic substrate, we're getting a less of an impact on the equivalent weight. So a lower equivalent weight, once again, means smaller spacing between these hydrophilic groups. And we see a stronger dependence on more hydrophilic substrates, and especially as we change the water content in the solvent. We can also look at this by just measuring the pH. When we do that, what we see is when we go to high water contents, we're getting lower pHs as we start to increase. And so what this is telling us is we have more accessible of these sulfonic acid groups at these higher water contents. So there's some kind of structural effect. And then similarly, if we look at dynamic light scattering, we see as we increase the water contents, we're getting smaller kind of aggregates or smaller particles. So schematically, what we're seeing is at kind of low water contents, high alcohol contents, we have these more blobs, if you will, with kind of internally embedded sites. As we start to increase water content, we're starting to open up the structure. As we go to very high water contents, we have a much more open structure with a lot more sulfonic acid sites that interact here with our hydrophilic substrates. So if we look at overall performance, what we see here is, if we look, this is essentially the surface coverage of the ionomer. It does increase as we would expect in terms of increased water content, once again, because we've opened up the structure. But if we look here at the resistance, we see that there's an optimal here. And similarly, if we look at these performance curves, there's also an optimum of kind of this middle range. And so what we're seeing is we're getting more kind of poisoning under operation as we go to hydrophilic. In this kind of middle range, we have enough open. In the larger range, we just don't have a good transport and good connectivity. We can also look at this in terms of, fixing the water content in the solvent, but looking at the different equivalent weights. And so as we change equivalent weights on a platinum substrate, which is what we were looking at before, and this is isothermal titration calorimetry, which gets us kind of the binding of the ionomer to the substrate, we see that as we go more hydrophobic or as we go towards lower spacings, we're getting less absorption. What's interesting is, with a more hydrophobic substrate, we're actually getting kind of an optimum somewhere in the middle here. And so what this is telling us is that there's a lot of also backbone absorption to hydrophobic substrates. And in fact, if we do a breakdown, what we see is it's really entropically and not enthalpically driven. And so then how does this start to relate to transport and overall performance again? And so here, if we're comparing this low equivalent weight to a high equivalent weight as a function of the ionomer to carbon ratio. So we can think of this as just increasing the amount of ionomer in our ink, and then we make a catalyst layer and test it. And so if we look at this catalyst layer resistance, we see at these low equivalent weights, we're getting more interactions at the interface, which is due to kind of that poisoning effect. But we have a more gentle slope, which is due to kind of a transport effect. And so once again, there is kind of this trade-off. What's actually interesting, though, is if we look at the performance and the resistance, we're getting kind of these linear to nonlinear transition regions. And this occurs at different critical ionomer contents or ionomer to carbon ratios. What we see, though, is we can actually normalize that. And so if we normalize for the sulfonic acid loading, so taking into account the equivalent weight, we see that there is this critical ratio where we go from this linear to nonlinear regime. And so what does this mean practically? And so within the ink, we measure the zeta potential, which tells us kind of about the stability. And once again, we're seeing that we get kind of this linear regime when we're in this saturated or unsaturated regime, and then we get kind of a change. And so as we start to get a lower magnitude of zeta potential, this is telling us that we're getting larger aggregation within the inks. And this is actually what's seen here in the TEMs. Similarly, we can actually look at this as kind of a titration curve, such as we increase the ionomer carbon ratio, we're starting to create monolayers on the surfaces, and then we just start to add in ionomer into the bulk solution, which essentially is just increasing the ionic strength of the material and acting like adding an acid. And so then if we look at performance, we see that aggregation in these different structures are what's driving this. So here, once again, is the zeta potential shown here. Here, we're actually looking at different platinum water content or weight percents as well. But what we can see here is we get this increase in the resistance as we're getting to kind of this nonlinear regime, which is also driven by the fact that we're getting this increase in resistance to the overall transport through the system and the platinum weight loading as it works within this to determine the structure. And so in summary, what I tried to argue was, the ink interactions are very critical. The adsorption is dependent on, obviously, the solvents, but also the ionomer equivalent weights, where we see surface affinities are much stronger for higher equivalent weights. We see some adsorption due to primarily hydrophobic interactions, where if we have excess ionomer, then that just acts as an acid and causes aggregation within the inks itself. As we make catalyst layers, we're getting worse performance because of that, because of the way that the ink interactions dominate the morphology and the structure, and looking at a local resistance, which really controls overall performance by both an interfacial as well as a transport resistance. And so the next step would be able to tune these interactions and cell performance by changing the ink properties once we understand fundamentally what's occurring. So with that, I'd just like to thank your time. And this was all funded under the Million Mile Fuel Cell Truck Consortium by the Department of Energy of the US. Thank you.
Professor Weber, thank you for your excellent talk. If you have any questions, please just type your question in the chat. The last speaker of this session is the Professor Clara Pereira from the University of Porto. Professor Clara, could you please start sharing?
Okay. Okay, so good morning, good afternoon, or good evening. In my country, it's good evening, good afternoon. My name is Clara Pereira, and I will be presenting the talk entitled Hybrid Smart Textiles and Devices for Energy Harvesting and Storage, Nanotechnology in Motion Towards Self-Powered Technologies. First of all, I would like to thank the organizing committee for the invitation to present this talk. To present myself, I'm an auxiliary researcher at the Associated Laboratory for Green Chemistry, Requinte Lacavia, which is the largest network in sustainable chemistry and chemical engineering of Portugal. I work at the University of Porto at the Faculty of Sciences in the Chemistry and Biochemistry Department in the research group Materials for Sustainability and Wellness. Our research group has a large expertise on the development of functional and smart bulk and nanomaterials with fine-tuned properties through green and cost-effective routes. These materials are developed for several target applications, and in this talk, I will be talking about our work towards smart textiles for energy storage. So, as we all know, we live in the era of the Internet of Things, where newer and smarter technologies are emerging every day for a myriad of applications ranging from healthcare, sports, defense, fashion, and transportation. Wearable technologies are indeed very important nowadays, and it is anticipated, according to the latest market reports, that the areas that will benefit the most from wearable technologies are home and lifestyle, military, medical and healthcare, sports and fitness, and fashion. So when we think about wearable technologies, one important question that we need to ask is how can we store energy on textiles in order to power these smart technologies integrated on clothes? The commercial solution that exists nowadays are batteries that are still rigid and need to be attached to specific positions of the garment, as we can see in this photo here on the left side. Moreover, they are composed of lithium, which is still harmful to the environment. And when we talk about wearable technologies, safety is of prime importance. Moreover, as we know, the batteries of our laptops, of mobile phones start losing efficiency with time, and so it is very important to overcome this disadvantage. So one alternative energy storage solution that emerged are supercapacitors, which present faster charging than batteries. So this means that we are able to reduce the charging time from hours to minutes or even seconds when we compare with batteries, and they present longer cycle life. Nevertheless, they still have lower energy density than batteries. So this means that they are a good solution if we have low energy consumption devices, namely sensors to monitor vital signs. Basically, there are two types of supercapacitors: electrical double layer capacitors or pseudo-capacitors, depending on the charge storage mechanism. If it is only based on the absorption or desorption of electrolyte ions at the electrode surface, we are talking about electrical double layer capacitors, while if we have the occurrence of redox reactions, we have pseudo-capacitors. So the main target nowadays has been to bridge the gap between batteries and supercapacitors and merge the advantages of both technologies in a single one. And so hybrid supercapacitors emerged, aiming to have higher energy density than supercapacitors and higher power density than batteries. In my country, the textile industry is one of the core engines for economic growth, and it is very important to develop innovative products using low cost and eco-friendly manufacturing processes, non-toxic components, and natural fabrics and fibers as substrates. And so we have been working directly with the textile industry in order to develop the energy storage solutions having these conditions in mind. And so one of the first works that we developed were textile supercapacitors composed of cotton fabrics as substrates and using commercial industrial grade carbon nanotubes as active electrode materials. We developed textile supercapacitors with different dimensions, and we used a deep coating, a deep pad dry method in order to incorporate the multi-wall carbon nanotubes in the cotton fabrics. Since this process is very used in the textile industry in order to dye textiles. And so through scanning electron microscopy, we could confirm that the cotton fabrics were well coated with the carbon nanotubes, and through X-ray diffraction and Raman spectroscopy, we could confirm that the structure of the carbon nanotubes was preserved upon their incorporation on the cotton fabrics. Afterwards, we assembled the textile supercapacitors. We used a solid gel electrolyte of polyvinyl alcohol doped with orthophosphoric acid. For wearables, it is very important to use solid gel or solid electrolytes. And we sandwiched these electrolytes between two electrodes of cotton coated with the multi-wall carbon nanotubes. We developed textile supercapacitors with different areas, and we could see that we could tune the energy density and power density depending on the dimensions of the textile supercapacitor. And so we could see that the device with the highest energy density was the device with the largest dimensions, whereas if we wanted to have higher power density, we should select the device with the smallest dimensions. Then we compared the performance with literature, and we could see that the performance of our device surpassed that of other electrical double layer type supercapacitors composed of natural cotton and natural textile substrates and carbon-based materials. And the performance was also compared with that of other types of hybrid type textile supercapacitors. In terms of cycling stability, which is also a very important characteristic, we could see that we could have a capacitance retention of 96% for at least 5,000 cycles. Afterwards, we evaluated the real performance when powering an LED as well as a sensor and humidity sensor, and we could see that in both cases we could see that our device was efficiently powering this type of devices. Then we scaled up the dimensions of our device and we developed a supercapacitor with 14 square centimeter, and we could see that when we charged the device for only 1 minute, we could power this sensor by almost 1 hour. So nowadays we are working with the technological center of the textile and clothing industry of Portugal, and we are scaling up this technology using their equipment. So nowadays we are working on boosting the energy storage performance, and one strategy to do that is to use redox active electrolytes. So our main goal was to develop a multifunctional fluorescent textile supercapacitor that combined energy storage with fluorescent properties in order to develop the safety clothing for nighttime users. We can use both fluorescent or phosphorescent pigments to do this. And so, in this case, we used again multi-wall carbon nanotubes coated on cotton fabrics as electrodes, and we used a zinc sulfide pigment doped with manganese cations as our redox active component. This pigment is composed of spherulite and wurtzite zinc sulfide phases, as we could see by X-ray diffraction. And through X-ray photoelectron spectroscopy, we could confirm that both manganese and zinc were in the 2+ states. Then we incorporated that pigment on the electrolyte, also of PVA doped with orthophosphoric acid, and then assembled the device in a sandwich type configuration. Remarkably, when we radiated the device with UV light, we could see the appearance of a very bright orange fluorescent color, which confirmed the existence of fluorescence. Afterwards, we examined the energy storage performance, and so here we can see the IV cycles, and we can see that the IV cycle of the device containing the fluorescent pigment had 2 redox humps over here, which confirms the existence of redox reactions in this type of device. In contrast, the device which contained an undoped electrolyte, which is this curve in black, didn't have these redox humps. Then we determined the energy and power density, and we could see an enhancement of 48% on the energy density and of 74% on the power density when we compare with the device composed of only carbon nanotubes. So we were able to improve the outputs by using these redox active electrolytes. When we compared with literature, we were also able to surpass the performance when we compare with other type of textile supercapacitors based on non-conductive fabric substrates and carbon materials. In terms of cycling stability, we preserved 100% of capacitance by at least 8,000 cycles. Then we evaluated this practically, and so in this video you can see our device on the upper part, which is being irradiated with UV light and is simultaneously powering this timer and temperature sensor. Here the mobile phone is only acting as chronometer. So what we can see is that the sensor is working, and while the device is being irradiated with UV light. So this means that the irradiation with UV light does not compromise at all the energy storage properties of our device, even by performing several charge and discharge cycles. Then another strategy to boost the energy storage performance is to endo redox active properties to the electrodes and not to the electrolytes. And so we did that using a flexible paper, because we are using different types of flexible substrates. And in this case, our active material were carbon nanotubes doped with nitrogen, which were functionalized with magnetic nanoparticles of magnetite, manganese ferrite, and also cobalt ferrite. Through transmission electron microscopy, we could see that the carbon nanotubes were very well coated with very tiny nanoparticles ranging from 3 to 5 nanometer size. Then we assembled the device, and we could see that the device with the best properties was one that was asymmetric, and on one side had paper coated with carbon nanotubes functionalized with magnetite, and on the other side carbon nanotubes functionalized with manganese ferrite. In this case, we had an enhancement of 6 times on the energy density and 1.4 times on the power density when we compared with a symmetric device composed only of carbon nanotubes doped with nitrogen. If we wanted to increase the power density, the best device was a symmetric one, which had on one side carbon nanotubes functionalized with cobalt ferrite nanoparticles. Nowadays, there is a major quest for all-in-one energy storage and harvesting technologies to meet the demands of the next generation that is emerging of autonomous self-powered wearables. And so we have been working in this field by merging thermal energy harvesting with energy storage supercapacitors within the same device. Our main goal is, as we can see in this picture, is to harvest the thermal energy released from our body, convert it into electrical energy, which is then stored within the same device. And bearing that in mind, we used a flexible PET substrate where we printed carbon nanotube electrodes in a hairbrush geometry, and then coated both electrodes with an electrolyte layer in order to have a planar device. Then we evaluated thermal energy harvesting, and what we could see is that when we increased the temperature difference between both electrodes, we were able to generate higher and higher output voltage. And so we were able to achieve output voltages of up to 45 millivolts. Also, we were able to have a harvest energy density of 118 nanowatts hour per square centimeter. The same device was also able to store energy, and in this case we had an energy density of 0.84 microwatts hour per square centimeter. So this means that since the harvest energy is lower than the stored energy, this means that if we are able to harvest more energy, the device has the capacity to store that energy, because we are talking here in terms of stored energy of almost 1 microwatt hour per square centimeter. And how does this technology work? Basically, you need to have 2 electrodes at different temperatures, and this will lead to a thermally induced diffusion of the electrolyte cations from the hot to the cold sides. Since we will have this disequilibrium on the electrolyte side, we will have electrons flowing from the hot side to the cold side through the external circuit. And so this will lead to an accumulation of charges on the electrode surface, and consequently, we will have stored energy within the same device. We have a field patent in this process, not only on plastic, but also on textiles. And so here you are seeing a t-shirt which has concentric electrodes printed on it. Here we are monitoring the output voltage. And so what we see in this video is that if we touch in the middle electrode, we are having a temperature difference between the center electrode and the external one. And automatically we have an output voltage being generated. Besides working with these printed electrodes, we also have we are using the whole surface, and in this case, since you have a larger contact area, this means that you have higher temperature difference, and so a much higher temperature output voltage. So this is still a work in progress, and we are continuously working on development of new electrode and electrolyte materials, self-chargeable multifunctional textile-based technologies, and also working in parallel in technology transfer and scale up with our technological transfer center in Portugal. And so I would like to thank all the team without whom this work wouldn't be possible, namely PhD students Rui and Joana, junior researcher Ana, and Professor André Pereira. I would like to thank the funding institutions, and of course, thank you all for your kind attention. And if you have any questions, please feel free to contact me. Thank you.
Professor Pereira, thank you for your wonderful talk. If anyone have any question, please just type your question in the chat. Okay, thank you all for participating and giving the wonderful presentations. And I myself surely learned a lot today, especially it's my first time to be the moderator. This would be the end of this session. we're probably going to, we can only have 1 minute break. Feel free to stay here for the next session. Next session will start at 10:20. Thank you.
Thank you for Dr. Chu for your hosting.
Hello, thank you, Dr. Webenchu, for chairing our first session, and welcome to Dr. Hemai Zhang for the second session chair. So now you can proceed, Dr. Hemai.
Okay, thanks. Hello, everyone. I'm Jaime Zhang from Lawrence Berkeley National Lab. And I'm going to chair this session. We have a series of speakers, and the time is very tight for each speaker. I hope you can be strict on time.
Sorry, Professor.
Yes. Can you hear me?
Oh, yeah, it's open now.
Sorry. If anything, I hope now it's better. I'm just trying to move a little bit. Maybe my internet is stronger this way. I hope you can hear me. So our first speaker, can you share your screen, please? Professor Dong-Chu Kim from Hanbat National University. Dong-Shu, are you here? Well, I didn't see our first speaker. Well, if not, if the speaker is not here, and we have a little bit of time for the break, especially people may need a short bio break. We just finished the first session. Then the next talk would be start. So if I also wonder, so sorry, maybe I'm making a mistake. If speaker's not here, let's see whether we can have the recorded session already. I apologize. I'm trying to check whether the online and the speakers already have the recorded session already. How would I play the recording? Any assistant?
Hello, Professor Zhang.
Yes.
The first speaker didn't provide a video, so we can now play the video of the second speaker.
Oh, I apologize then. Well, let's be on time. Let's start at 10:30 when we play the second video, so that people intended the schedule to attend, so they don't miss the talks. Thank you for letting me know. And sorry, I'm trying to get familiar. You, Jian Yuan?
Yeah, it's me.
Jing Yuan, I'm sorry, Jing
yeah.
Yuan. Jing Yuan, the second speaker would be playing. We would be playing the video, right? Are you going to help with playing?
Okay, I can play.
Yeah, if I need to play, I can do it. I just wanted to see where is the play button.
Okay, if which one you want to play, you can ask me. I will share the video.
Okay, that's great. So let's be on time. 5 minutes later, at 10:30, we will start playing the second talk, the video. Thank you.
Okay.
Professor Cheng, I have a quick question. So
yes,
in the conference, do we have any time allocated for separate discussion, or is it just online kind of
yeah,
discussion?
so we hope that we would have a little bit time for the discussion. Otherwise, these are too packed talk. But I'm just checking on our calendars. It seems there's no panel discussion. Maybe Jing Yuan, you can help. Are you there, Jing Yuan?
Oh yeah, I'm here. Sorry, can you repeat the internet wasn't good just now?
Yeah, we would like to have a panel discussion after, because we really don't have time for questions. Do we? I didn't see the time allocated for these panel discussions and answer questions.
If someone has some questions, you can type in the chat, in the Zoom chat, and the speaker can answer in there.
Separately?
I think
individually.
You can chat to everyone. It's just like a group.
Okay, so
just a minute, I can add like for this panel discussion, because this time we have a different time zones. So we create online account, like you can use the online account. There you can chat with any of the speaker, and you can use the mobile app as well, where you can create or you can chat with any of the speaker, and you can ask direct question to them, or you, if you want to communicate, you can communicate with them. Actually, we are facing this issue because the time zone is so different from throughout the world, and like many speakers, they just send us the videos, and they were not able to join online because there may be the midnight or maybe early morning. So that's the reason. But
Yeah,
we
you're
are
right.
open, like if you have any questions or anything that can be done either through online through your account, you can send it directly to any speaker and they can respond to you, or you can just type on the Zoom. We can ask those questions to the speakers. And if you're using the mobile app, there you can send the questions and that can be sent directly to the speaker to whom you want to ask. So maybe the speaker, maybe you listen the talk, maybe the speaker is not online, we are just playing the video. So that's the reason, like we don't have a separate discussion panel this time. Otherwise, every year we have on campus and we have the panel discussion separate.
Thank you. And your name is?
Dr. Shakir.
Okay, thank you.
Thank you. We will just start our second talk of this session.
Okay, I will share the screen.
Jingyang, can you?
Oh yeah, I can
Thank
share
you.
the screen.
Hello, I will present now a metamaterial made supercapacitor that harvests nuclear particle kinetic energy and delivers it as electricity as a new development in engineered nano micro materials with that improves nuclear power production. And if that happens in my nano heterostructure, we call it CI-CI or GG, where a particle is passing through and produce a lot of equal energy, we'll end up with removing all the thermomechanoelectric cycle, having the nuclear reactor that generates directly electricity. And you know, it's very important because nuclear power is by 6 orders of magnitude more compact than any other chemical power source. The power sources are more compact, are smaller, and give 1,000,000 times more energy. Here is how the process takes place when the particles come into a layer that have a lot of available electron. It creates a large shower that flies ballistically through an insulator, say Teflon, and then is stopped into another element that the conductor one, maybe aluminium, and here it creates a negative charge, while the layer with the electron left, it becomes positive. And if you measure the materials, you'll see that elements like gold, radium, have good electron availability and are good for one layer. The others are good for collecting layer, and some are good for insulator. And here is how the local electrons are creating electron shower in the first layer and are ballistically tunneling the insulator and are stopping in the third layer in a simulation Monte Carlo code. Here is how it happens. Efficient products goes along the layers and produce big showers in the high electron availability layer, producing the voltage and the current, and that is collected in as a conductive layer and put into a load resistor. From the point of view of material capabilities, it's huge. We can put on a material on a cubic millimeter about 5 kilowatt per cubic millimeter. Even more if we have a superconductive structure. But the devil is in the details because conversion efficiency matters, and each constructive has its maximum efficiency. So this is a spherical beaded structures that efficiency may go up to 90% or more. And this is a planar structure where the conductive layers are connected in parallel, like a parallel capacitor. And that has a 60% limit in maximum efficiency due to the solid angle. And this is a planar connected in series, and various evolutions from this planar to embedded nanobeads, the gold nanobeads suspended in silica, and advanced solution using nanotubes with longitudinal conductivity and transversal non-conductivity embedded into a lithium hydride, combining the effect of a high energy generator with low energy collector. There are many applications in space, like corpse antennas for remote IMD teleportation, shielding, and for cosmic particles with energy conversion. The most near application is to make radiation batteries, included in alpha and beta voltae, making force that will be about 50 microns thick. This is a half. And here is the fuel, the plutonium-238 or polonium-210 that generates alpha particles that produce electricity. Here is how the power density is varying with the type of isotope we are using. We may use alpha and beta successfully, but no gamma because they have very low stopping power, and even they have a good density like cobalt 60, the dimensions will be huge for the battery, and instead of having a microfoil end up in centimeter. This is the powers for a plutonium-238 and polonium-210, and these are the minimum dimension for a battery, and that has the power for the minimum dimension. So if we turn them towards the center back into the nuclear reactor, we increase criticality, but if we leave them go away, we may decrease the criticality and increase the transmutation production. And we may use nano switches that have response time in microseconds, controlling the reactor and using the probe neutrons. And this is some application we can do with that. And these are various types of shielding with a classical called mass attenuation, because no matter what material you put, for getting some attenuation level, you'll end up with about same mass. Most power, like quantum scattering, that turns directed energy into 4 pi quasi energy, reducing the intensity of one direction, and quantum absorption and re-emission that is doing this effect. On the other side, we can use body shielding and electronic shielding to avoid electronic upset in radiation fields, and we can build a solid-state nuclear reactor, no moving parts, and only the electronics will control the criticality versus the absorption of the neutrons. So all the neutron balance and the neutron economy will be electronically controlled. And that will make the reactor smaller, being able to be put on even SUV. This is what we are talking about, and that will be possible to be achieved after using all these 5 families of nanostructure in a synergistic way in order to have a efficient battery. That will be smaller, will reduce the full power plant of today into a trailer, and will allow us having a lot of fancy application that's flying spaceport, autonomy of more than several years for strategic airplanes, subways, and trains powered directly with energy. We can stop wars because we may use as power supplies for directed energy devices in outer space, able to shoot down even on terrestrial and deny even the cannon projectiles. Well, these are the materials that may trigger the leap and depend on us of how we see the future. We are looking to what remains after the actual nuclear power plant of monuments of failed technology and end up with a lot of capability of self-destruction, or we'll end up learning how to use plutonium and fission material, high fissile materials in the same way we use a gasoline today, making flying vehicles, propulsion, stop the wars, and focusing on the important stuff, colonizing our solar system and having a better planet. Now, as Albert Einstein and Niels Bohr once talked about and thought, any fool can know. The problem is to understand. And if we understand and we have a new knowledge, we'll have a lot of new questions we need to answer and understand it.
Jingyang, can you stop the sharing? Thank you. Well, we thank the second speaker sending the recorded video. Anybody have questions, please type into the chat. Our organizing committee can collect all the questions. And at this time, we wanted to, the time is very tight in the schedule. We would need to move on. And our third speaker is George Adrias. Taras, are you here? If not, Jingyang.
I'm here, but I'm unable to present. So if you could play the video, please.
Oh, I see. Thank you, Andreas. Jingyang.
Okay.
Hello, my name is Andres Guerra and I work at the Catholic University of Peru. Today, I will be presenting our results concerning the bandgap engineering of amorphous hydrogenated silicon carbide thin pins for photoelectrochemical water splitting applications. I'd like to start this presentation by highlighting that hydrogen pin production, as well as the research on photoelectrochemical devices, has gained increased attention in the past decades. Additionally, fuel cells have already achieved efficiencies around 75%, and they are already available commercially. Whereas photoelectrochemical devices have achieved different technologies of photoelectrochemical devices have already achieved efficiencies around 60%, making them attractive for commercial applications. So in the case of the materials used in semiconductor-based photoelectrochemical devices, they should fulfill certain requirements like high chemical stability, low overpotentials, a nice band edge position to drive the reactions, as well as the material should be abundant and cost effective. Also, the band gap of the material should be high enough in order to be able to drive the reaction, as well as low enough to have a sufficiently high photocurrent in the case of using sunlight. Among these materials, silicon carbide has been used already as photocathode in photoelectrochemical devices. In particular, one can change the optical bandgap of this material by changing the stoichiometry of the material. However, by changing the stoichiometry, one can hinder its chemical stability and also the band edge position alignment. Therefore, what we would aim in this work is to tailor the optical properties and the optical bandgap of this material by changing the hydrogen content, as well as by performing post-deposition thermal treatments. Now, the question arises on how do we determine the optical bandgap of an amorphous material. Here I'm plotting the tau plot for the absorption coefficient in the tau scale, that is the square root of the absorption coefficient multiplied by the photon energy versus the photon energy. And by using the tau model, one can determine easily the optical bandgap. However, in amorphous materials, this determination can be biased by the presence of large Urbach tails. These Urbach tails can be modeled by the so-called Urbach rule. We have developed a model based on band fluctuations which can actually model the whole fundamental absorption, that is the tau region as well as the Urbach region in a single equation. Although the equation looks a bit alien, we can find certain known parameters like the Urbach energy as well as the optical bandgap. Also, this function is called polylogarithmic function of order 2, and is nothing more than a representation of a Fermi integral. If you are interested in knowing more about this model, please visit a paper we published a couple of years ago. We have grown samples with 4 different hydrogen dilution conditions during the deposition process. 1 without hydrogen and 3 with increasing hydrogen contents. From optical transmitted measurements, we have determined the thickness, refractive index, and absorption coefficient by a method developed also in our group, in a way that we do not use dispersion relation to model the absorption coefficient. Here on the right, I'm showing you the absorption coefficient of these samples in the strong state in the tau scale. Red lines correspond to fits performed using the band fluctuations model, whilst the black dotted lines correspond to fits using the traditional tau model. Remember that this model, the tau model, does not take into account the presence of Urbach tails. Now here I'm showing you the tau gap versus the annealing temperature for these 4 different samples, as well as for comparison purposes, the E04 absorption bandgap. And on the right, I'm presenting you the optical bandgap determined with the band fluctuations model. We see several features, but first, it seems that depending on the model we use, we might have a material with a bandgap inside or not the sweet region for a photoelectrochemical device. In particular, the variation of the optical bandgap with the annealing treatment in the case of hydrogen and silicon carbide has been attributed to the outdiffusion of hydrogen. However, we see the same behavior, that is an increase and a decrease of the bandgap in the case of a sample grown without any hydrogen dilution. We believe that this variation is actually related to change in the structure. And for this, we have also performed FDR analysis on these samples. We focus on the sample grown with 3 SCCM flow of hydrogen because it's the one that has the closest bandgap to the region, the suitable region for the photoelectrochemical application. And also, it has hydrogen, which improves its electrical properties. From the absorption coefficient in the infrared region, we determine the bond density, and we see how, in fact, the carbon-hydrogen and silicon-hydrogen bonds are quenched with annealing treatments as expected. Also, from the silicon-hydrogen bond frequency, we are able to note that there is a change in the environment of the silicon-hydrogen bonds related to the increase of the silicon-carbon or the creation of new silicon-carbon bonds. Here I'm showing you the measure of the full width maximum of silicon-carbon bonds from FDR measurements for the 4 samples versus the annealing temperature, as well as the Urbach energy determined with the band fluctuations model. We see a similar trend, a similar behavior in both cases. The Urbach energy, as well as the full width maximum, is related to change in the structure of the material. This sample experiences a thermally induced densification. We can see this directly with SEM measurements, as well as by measurements performed with optical transmittance. We see how the thickness or the relative thickness is decreasing with increasing annealing temperature. We also see that if we plot the optical bandgap versus the mass density, we see that the bandgap increases with the mass density as expected. So, and to be sure, we also perform in a different group of samples drawn in a similar fashion, X-ray reflectometry measurements of these samples after different annealing temperatures. And we see how the thickness is also decreasing, as well as the measured mass density is increasing. So we believe that the shift we observe in the optical bandgap with the hydrogen dilution is actually related to a densification of the material. When the hydrogen is introduced in the material during the deposition process, it pacifies dangling bonds and reduces the volume these dangling bonds are occupying, thus reducing the mean lattice constant. Also, the shape these curves have with the annealing temperature in the case of the tau bandgap and the E04 bandgap is actually linked to the Urbach-Henry. As we said at the beginning, the Urbach-Tails bias the determination of the optical bandgap with these models. It's easily to show that this is the Urbach rule, here written along with the Urbach focus, E0 and alpha 0. And the bandgap falls within the range where the absorption coefficient can be modeled with the Urbach rule. You can write the optical bandgap determined either with the tau plot or the E04 method in terms of the Urbach-Henry. That is, when the Urbach-Henry increases, it will show a decrease on the optical bandgap. Additionally, we know that this variation is related to change in the structure. For this, we perform Raman measurements, and we see that the silicon bonds are quenched more rapidly than the carbon-to-carbon bonds. Also, carbon-carbon bonds are quenched and then increase again. Finally, we grow photocathodes with these silicon carbide layers grown under these hydrogen dilution conditions on top of p-type silicon substrates. Out of linear sweep voltammetry, we were able to show that it is possible to drive the reaction, in particular for a sample annealed at 600 degrees Celsius. And we also perform a Mach-Schottky analysis. From this Mach-Schottky analysis, we are able to determine the flat band potential as well as the space charge region, ranging between 390 nanometers and 435 nanometers, which is around the thickness of the silicon carbide layer. Therefore, establishing that there is also absorption through the silicon substrate. The variation of the slope is actually related to the variation of the electron constant with the frequency. We're still still studying this system and trying to find a suitable equivalent circuit in order to perform a better analysis of the capacitance. So this will be all from me, from my part. Thank you very much for your attention, and these are the institutions that are supporting us. Thank you very much.
Well, thank you for our speaker here. And if anyone have questions, please type in the chat. Again, sorry that we won't have time for direct answer questions, but our speaker is here, and all the typed messages should share to everyone. Now we start our next speaker, Wenbin Chu. He will be talking about peculiar defects behavior in charge recombination of metal halide perovskite. Wenbin from University of Southern California, please.
Thanks for the nice introduction. Good morning or good evening, everyone. I'm Wenbin Chu from the University of Southern California. I'm glad to have this opportunity to share with you about our recent progress to understand the defect behavior in metal halide perovskite with theoretical simulation. As we all know, metal halide perovskite is a wonderful material in the recent year, particularly because their strong defect tolerance. Defect, especially the deep level defect, are believed to be a bad recombination center, which limits the solar cell efficiency. Recently, people found this metal halide perovskite shows 3 advantages among all solar cells. First, this material has a high absorption, thus we can use a thin film to absorb the light. Second, this material is totally different from the conventional organic materials. This material has a long diffusion length. which means that the charge carrier induced by the photon can be very efficient. Third, this material is synthesized in solution, which means that it should have tremendous defect. However, the carrier lifetime is super long. Considering the abundant defects, this material should have strong defect tolerance. The previous theoretical study found the dominated defects in these materials are shallow defects. The deep defect has high formation energy. However, it cannot explain the extraordinary efficiency of metal halide perovskite, even there are tons of defects. The defect always plays an important role in the solar cell efficiency because the defect level in the band gap or near the band edge can assist the non-radiative electron hole recombination in the semiconductor. And this is considered to be the bottleneck of the solar cell efficiency. In 1950, Shockley, Reid, and Hall developed this well-known SRH model to describe this defect-assisted recombination. They consider the localized defect state in the band gap can assist the non-radiative recombination. SRH model reached greater success and has been widely applied for different kinds of semiconductors, including perovskite solar cell. It provides a simple judgment that deep level traps in the band gap are believed to be an effective electron hole recombination center, and this is harmful to the solar cell. However, SRH model is focuses on giving a microscopy statistic. When we came to an initial or atomic level, what is non-radiative recombination? It's the electronic energy dissipates into heat, which is assisted by the phonon. So the electron-phonon interaction should be considered, should be the dominant factor in these processes. However, these interactions are not explicitly included in the original SRH model. Our group developed the method using non-adiabatic molecular dynamics, which employs time-dependent constraint theory with the surface scoping framework to study this non-radiative recombination in real time. Generally, the evolution of electron hole recombination is governed by the non-adiabatic coupling, which can be get through solving time-dependent Schrödinger equation. Generally speaking, if the electron-phonon coupling is large or the gap is small, the recombination will be fast. So that's why SRH model works for most semiconductors. Defects reduce the energy gap. However, defect electron is always a localized electron. Thus, the overlap and electron-phonon coupling should be smaller in the defective system. Definitely, it's sensitive to the type of defect. One can expect if the electron-phonon coupling term decreases sufficiently, in other words, it can compensate the small gap introduced by deep level defect, then the final recombination rate should be comparable to those in pristine. It means the deep level defect then becomes not harmful as predicted by SRH model. That's what we're going to discuss later. As mentioned earlier, this material is prepared in solution. It means this material should have tons of defects. However, the efficiency of perovskite progresses like a rocket in recent years. So perovskite should be strong defect tolerated. We have studied a bunch of defects in both hybrid and all inorganic perovskite. Some of them are deep level defects and some are shallow level defects. Surprisingly, we found the non-radiative recombination for all those defective systems in our simulation, regardless of whether the defect is a deep level or shallow level. The final recombination rate is comparable to the pristine system. Moreover, in the all inorganic perovskite, all defects investigated here suppress the recombination. It's really amazing. Meanwhile, we found some defects that exhibit strong covalency. Halide perovskite is an ionic material. The iodine trimer, which is a covalent bond, is very rare. Previous study also found this formation of iodine trimer in hybrid perovskite. They found the formation of this covalent bond will lift up the defect energy level in the band gap. Then this shallow defect turns into a deep defect. The previous study predicted this defect as a strong recombination center based on the simple SIH model, just because the energy level is at the middle of the band gap. However, in our calculation, the recombination is suppressed by those iodine trimmer. To understand this, we need to study this defect electron at real time and at the initial level, which means the incorporation with a phonon should be considered. Here is a statistical distribution of nuclear and defect electron or a 10 picosecond dynamics. One can see the defect atom is located in a small region, and the electrons are strongly localized near the iodine trimmer. There is a rare distribution or even zero distribution on the inorganic lattice in both cases. By doing the Fourier transform, we can know which phonon mode contributes to the electron-hole recombination. One can see all these phonon that contribute to electron-hole recombination at low frequency, and we think this is the main reason for the strong defect tolerance in perovskite. And it can be understood by comparing with the conventional semiconductor. The defect electron is more localized in this soft semiconductor compared to the conventional high-frequency semiconductor. Here is a 3D version of previous statistical distribution of the defect electron into typical semiconductors. One can clearly see the electron strongly localized in a small region in perovskite. We think this situation that the electron strongly localized behavior correlates with the low-frequency phonon is kinda similar to the Anderson localization. The low-frequency lattice phonon, the small bulk modulars in these soft materials, indicate a strong disorder, and the electron getting localized due to the disorder. Finally, we come to the conclusion. Thanks for your time. The main point we want to claim is the electron-phonon coupling is very important, and you cannot ignore it when considering non-radiative recombination. We propose a scenario that the deep defect can be benign in non-radiative recombination. The defect becomes strongly localized when incorporated with the low-frequency lattice phonon. Thus, its overlap is small with the free carriers, making it can win the battle with the decreased energy difference. At last, I would like to use this opportunity to thank my advisor and collaborators. The first work on the hybrid perovskite is supervised under my PhD advisor, Jin. And the second work on the all-inorganic perovskite is supervised under my postdoc advisor, Oleg. I would like to also thank my collaborator, Wissam and Qijing. At last, I would like to thank you for your attention. If you have any question, please feel free to contact me. Thank you.
Thanks, Weibin, for the excellent talk. And again, if anybody have questions, please chat. Type your questions through the chat. Our speaker is here. We won't have time for question session, but we are going to go directly to the next talk. And the next talk is a pre-recorded video from Professor Sung Jiang Kim from Hanyang University. Jian Yuan, can you please help to play the video? Jingyang, I don't hear the voice.
Sorry, I will start from the beginning.
Hello, I'm Sung Jiang Kim of Hanyang University. I introduced an energy harvester using carbonate ion in seawater for self-valve device. Artificial muscle has no muscle-like actuator materials or device that mimic natural muscle and can change their stiffness reversibly contract and expand or rotate within one component by external stimulus in Wikipedia. Many researchers are working artificial muscle, such as volume expanding, electrostatic artificial muscle, or bending ionic polymer metal composite artificial muscle. Our colleague and I discovered torsional artificial muscle using carbon nanotube yarn in 2011. Twist carbon nanotube yarn at left image. The torsional artificial muscle consists of twist yarn like a fiber. In the middle image, twist carbon nanotube yarn was charged in a 3-electrode electrochemical system. The yarn provides 50,000 degrees of reversible rotation. Artificial muscle was electrochemically charged. The carbon nanotube yarn showed torsional and tensile actuation and left image. Here, the carbon nanotube yarn artificial muscle was immersed in electrolyte and generated open circuit voltage at right image. This invention published.
These tiny twists consist of a carbon nanotube spring tied into a tangled weave of carbon, then submerged in a gel full of ions. When pulled, carbon nanotubes squeeze together, decreasing the electrochemical capacitance and thereby generating a small current, enough to momentarily light up an LED. This shirt has a pair of these twist-drawn yarns sewn in. When the wearer breathes in and out, a small amount of electricity is generated, which could be useful data for medical devices. More power can be generated if the harvesters are hooked up together, with peak power generation reaching 250 watts per kilogram. These carbon nanotube yarns may have applications anywhere reliable kinetic energy is available.
Twist energy harvester makes self-powered energy without needing an external bias voltage. At upper image, a stack of forest-drawn carbon nanotube sheet was rolled in the cylinder. C is twisted on the applied load to produce the yarn. D is subsequently twisted on the load to produce a coiled twist energy harvester. The coiled multi-weld carbon nanotube yarn mechanical energy harvester, called short twist energy harvester. At lower image, according to spin method, the yarn cross-section have several structures, such as the cone, funnel, ferment, diorachmic structure. At the left image, all electrodes are immersed in the aqueous electrolyte, such as hydrochloric acid, sodium chloride solution. We tethered the coiled carbon nanotube yarn energy harvester as a working electrode in an electrochemical vessel, showing the coiled sheet carbon nanotube yarn before and after stretch. And right image, according to state, the capacitance decreased and the voltage increased. When stretched at 30% strain, the carbon nanotube yarn energy harvester capacitance decreased 30%, and its open circuit voltage increased by 150 millivolts. At upper image, we tested to harvesting the energy of near shore ocean waves. The harvest was immersed in Gyeongpo Sea of South Korea. The yarn attached between a balloon and a sinker at seabed during ocean wave harvesting generate peak to peak. At low limit, organ with body, human serum, normally water solution could be used as electrolyte in this energy harvesting. So twisted energy harvest has a potential application in biomedical field. At the left figure, we test the liquid electrolyte as well as gel electrolyte. There is nearly no hysteresis between liquid electrolyte and solid electrolyte. This has a potential application in wearable technology. At the right figure, we pair of these homocular and heterocular was stretched so it meets the cotton glove and separated over coated with the PVA rich chloride gel electrolyte. When connected parallel and series at 50% state, measured open circuit voltage and peak short circuit current. We demonstrated an application for powering a LED when stretching a coiled carbonate yarn to 13% strain at a half hertz in hydrochloric acid solution. One 3-strand energy harvester fiber generated 2.8 voltage connected with boost converter circuit. In 2018, we exhibited in Nana Korea fair in South Korea. That time, the twisted energy harvester powered LED in seawater. In 2019, we showed self-powered energy signal accuracy shield. In 2019, consumer electronic shows in Las Vegas. Usually, these shows were some aqua shows, but in case of emergency, LED-powered signal drive by electrical energy harvesting. Electrical energy harvesting is generated by reversibly stretching of yarn in seawater. These self energy signal aqua show, we got innovation award in wearable technology. I think the twisted energy harvester has so many potential applications in every industrial field as a power source, such as drone, smartphone, medical device. I thank you, researcher in our group and Professor Ray Bama. Thank you for your attention.
Thanks, our speaker, for the type in through the chat, and we are going to, unfortunately, no time for it, for a question, answering questions. We are going to the next speaker, Mien and Yu from Multimedia University of Malaysia. Please.
Hi, a very good morning to the session chair and everyone. My name is Mian Eng, and today I would like to present my research with the title Synthesis of Anatase Rutil Mixed Space, named dioxide photoanode for the dye-sensitized solar cells. In light of the growing demand of energy, depletion of the fossil resources, as well as the global warming and associated climate change due to the combustion of the fossil resources, the scientific community has reckoned the development of renewable energy as one of the important challenges to be addressed by the mankind. And among all the renewable energy, solar energy is particularly attractive due to its abundance and cleanness. Dye-sensitized solar cells, or DSSC, is one of the third-generation solar cells or emerging type of photovoltaic technologies that was first developed by Michael Glaser and Brian Oregon in 1991. There are numerous attractive features offered by the DSSC, such as the low production cost, versatile fabrication process, ability to operate in low light conditions, as well as semi-transparent. Next, I will discuss briefly about the operating principles of the DSSC. Upon the illumination and the photon absorptions, the dye molecules will be photoexcited from the ground state to the excited states, followed by the injection of the electron into the conduction band of the semi-conducting metal oxide, typically the titanium dioxide layers. The electron will then diffuse across the TiO2 matrix to the FTO substrate to the external load before going back to the counter electrode. And concurrently, the oxidized dye molecule is reduced by the redox couple present in the electrolyte and hence completes the whole cycle. Hydrothermal method is the most widely adopted technique for the synthesis of the titanium dioxide photoanode. Nevertheless, the reported processing steps for the hydrothermal synthesis of the titanium dioxide photoanode were intricate and thus complicated the overall DSSC processing. And in this work, we have developed a reinvented methodology for the hydrothermal synthesis of anatase rutil mixed phase titanium dioxide photoanode by omitting several intermediate steps, which can simplify the whole DSSC processing significantly. Here is a gradient flow chart of the hydrothermal synthesis of titanium dioxide phase for the DSSC. The left-hand side is a methodology as reported in the literature, while the right-hand side is a methodology as adopted in the current research. So as we can see here, the methodology reported in the literature involves several additional steps, such as this redispersion, the correct concentrations, centrifugations, phase homogenization, and etc., which requires the use of specific instruments such as the sonicator, rotary evaporator, centrifuge, and 3-row mills, which complicate the overall DSSC processing. And in this work, it was discovered that the titanium dioxide paste can be obtained simply by heating the solution after the hydrothermal treatment, which can simplify the DSSC processing significantly. And by using this simplified methodology, the DSSC with promising photovoltaic performance was propagated, which will be discussed in the following section. So as I mentioned in the previous slides, titanium dioxide paste was propagated by using the hydrothermal method. So first, the acetic acid was added to the TTIP, followed by stirring at room temperature, and the mixture was dropped into the DI water, followed by stirring to complete the hydrolysis reactions. And nitric acid was added into the mixtures, and the solution temperature was increased to 80 degrees Celsius in 40 minutes and held constant for 80 minutes under stirring. Next, the resultant mixture was kept in autoclave and heated at 200 degrees Celsius for 9 hours. And after that, the nitric acid was added to the colloidal solution, followed by stirring for the 50 minutes. And the last step is that the colloidal solution was heated at 35 degrees Celsius for 90 minutes to obtain the titanium dioxide paste. And here is a flow chart for the fabrications of a standard DSSC. So first, the FTO substrates were automatically cleaned in acetone and IPA respectively. Two substrates are needed to fabricate a single DSSC. One as the working electrode, and the other one is the counter electrode. For the preparation of the working electrode, the synthesized titanium dioxide paste was applied onto the FTO substrate by using the solar plate technique, followed by sintering at 450 degrees Celsius for 30 minutes. Next, the coated substrate was immersed in the N719 dye solution for overnight. The counter electrode was prepared by applying the platinum paste onto another FTO substrate using a similar solar plate technique. followed by synthetic at 150 degrees Celsius for 10 minutes. Next, both substrates were sandwiched together by using the binder clips, followed by the injection of the electrolyte. For the comparison purpose, the commercial titanium dioxide paste was also used to fabricate a standard DSSC, which act as a reference cells. Here is a characterization results and the discussions. For convenience, the hydrothermally synthesized titanium dioxide photoanode was abbreviated as HT9, while the photoanode fabricated by using the commercial titanium dioxide paste was denoted as the reference or IF. And from the FESCM images as shown here, the formation of the rock shell particles can be distinguished in the first figure, which can be attributed to the high rutile content of the HT9. And in the second figure, the agglomeration of the spherical anatase titanium dioxide nanoparticles can be observed, and no rock shell particle was visible due to the absence of the rutile phase in the reference. And in order to characterize the phase compositions of the photoanode, the X-ray diffractions or SRD characterization was also performed. In HG9, the P intensity of the rutile 110 plane was relatively higher than the anatase 101 plane. Which indicated that the HG9 was predominantly comprised of the rutile phase. Whereas in the reference cells, no rutile phase was present. And the high diffraction peak can be observed at the anatase 101, which indicated that the reference consists of pure anatase nanoparticles with a high crystallinity. The UV spectroscopy was also carried out in order to characterize the optical properties of the photoanode. As we can see from the absorption spectra here, the absorbance of the reference was higher than HG9. And in addition, both samples exhibited absorptions at below 400 nanometers, which can be ascribed to the band-to-band electron transmission in the titanium dioxide nanocrystals. And here is a photocurrent voltage curve of the DSSC integrated with the photoanodes, and the corresponding photovoltaic data was summarized in the table below. So from the photovoltaic data here, the short circuit current density of the DSSC based on HT9 was around 90% lower than the reference, which led to a lower PCE than compared to the reference. The reduction in the photocurrent can be attributed to the high rutile content in the HT9, which resulted in the decreased surface area. The high surface area of the titanium dioxide is essential for the efficient dye absorption, and hence the reduction in the titanium dioxide surface area will result in the lower photocurrent due to the poor dye absorption. So in conclusion, by using the reinvented and simplified methodology for the short-gel hydrothermal synthesis, the anatase rutile mixed phase titanium dioxide photoanodes were successfully fabricated and integrated into the DSSC. The efficiency of the DSSC based on the anatase rutile mixed phase titanium dioxide photoanode, which is 3.3%, was comparable to the DSSC based on the commercial phase at 3.81%, which demonstrated the applicability of the new methodology for the synthesis of the titanium dioxide photoanode. Further investigation into the optimum hydrothermal synthesis parameters, such as the hydrothermal duration and the hydrothermal temperature, was required in order to achieve the optimized photovoltaic performance of the DSSC. We would like to acknowledge MMU GIS Scholarship and the Telecom Malaysia Research and Development, TMI&D, for providing the financial sponsorship to facilitate this research project under TMI&D Research Fund 2017. Yeah, and that's all from me. Thank you very much.
A nice talk. Thanks. Thanks for the nice talk. Again, anybody have questions, please type in the chat. We are going to do the next talk from Professor Mila Warner from UT's Technical University, Istanbul, Turkey. If we are not doing a live, do we have pre-recorded video?
Hello.
Oh, we have a live session. That's wonderful.
Okay. I will present the topic instead of Professor Mualla Öner.
Okay, please go ahead
Okay.
and share your screen.
Okay.
Oh, that's good.
Can you see?
Yes, yes.
Okay. Good morning, good afternoon, good evening, everyone. Thank you for joining us today. My name is Seda Köksal, and I am Research and Development Executive in Parallel Company. I am a PhD candidate in Yıldız Technical University. I have experience for 11 years about fuel cell technology and ion exchange membranes. Today, as you can see on the screen, I would like to talk about synthesis and characterization of polyacrylonitrile nanocomposite for proton exchange membrane materials in fuel cells. This presentation is structured as follows: introduction, experimental results, and discussion. Now let's move to the first part of the presentation. What is polymer electrolyte membrane fuel cell? A fuel cell is a device that generates electricity by a chemical reaction. Also, I would like to share with you my previous studies: catalyst coating, membrane assembly preparation, liquid seal application, stack design and assembly, and fuel cell tests. Okay, so what is fuel cell membrane? Cationic properties of the fuel cell membranes are cationic ion conductivity, hydrophilic structure, non-permeable for hydrogen gas and oxygen gas, heat resistance up to 100 centigrade degree, low affection from weather conditions. Now we come to the next point, which is experimental section. Membrane solution preparation, electrospinning process, phosphoric acid process doping, phosphoric acid surface process doping. As you can see, membrane preparation materials on the screen. We used polyvinyl difluoride polymer, polyacrylonitrile polymer, dimethyl formamide solvents, phosphoric acid, fumed silica, and borax for preparation of the nanofiber membrane samples. Now, let's move to the next part of the presentation, electrospinning process. Electrospinning process is a fiber production method which uses electric force to draw charged threads of polymer solutions or polymer melts up to the fiber diameters in the order of some 100 nanometers. Properties: nanofiber structure, very high surface area, controllable thin membrane thickness, good mechanical strength, high strength to weight ratio. As you can see, our laboratory electrospinning on the screen. I would like to share you a video about separation of nanofiber membrane from foil. Okay. Also, as you can see, one of the samples are nanofiber membranes. The membranes has good durability. Also, I would like to share you industrial electrospinning machine. It is possible industrial nanofiber membrane production. All right, let's turn to membrane preparation. Now we come to the next point, which is membrane surface doping with phosphoric acid. As you can see, membrane samples in the phosphoric acid solutions for the doping, surface doping. You can see our membrane samples, nanofiber membrane samples and film membrane samples. Nanofiber membrane samples have a white color and opaque structure. Film membrane samples which produce same polymer, which is polyacrylonitrile, are transparent and white. There is not any problem on the surface. This leads to my next point, which is results. The spectra were recorded by Selectron electrochemical interface and impedance analyzer. Each sample was measured 3 times. The sample of the same material was immersed into water for 24 hours. The spectra were recorded within the range from 1 megahertz to 0.1 hertz. Okay, as you can see in this chart, nanofiber membranes were higher ionic conductivity than film membranes under same doping conditions. Also, under same doping conditions, nanofiber membranes with borax had a higher ionic conductivity than nanofiber membranes with fumed silica. Also, we had high water uptake results with nanofiber membranes. We plan to decrease additives rates for next study. Z-plot graphs shows resistance of the membranes for ionic conductivity. So, as you can see, polyacrylonitrile nanofiber membranes showed higher ionic conductivity than polyvinyl difluoride polymer membranes under same doping conditions. And both of these membranes had low water uptake. Z-plot graphs show resistance of the membranes. These graphs show the weight reduction of the membranes depend on temperature. We will continue investigate the thermal properties. If you look at this big graph, you will see fiber diameter of the nanofiber membranes with additives. Let me show you surface morphology of the nanofiber membrane with additive. As you can see, nanofiber structure is obtained. To sum up, membranes produced by electrospinning method have higher ionic conductivity than membranes produced film method. Nanofiber membranes produced from polyacrylonitrile polymer showed higher ionic conductivity than the nanofiber membranes produced from PVDF polymer. Under the same doping conditions, the nanofiber membrane containing 3% borax showed higher ionic conductivity than the nanofiber membrane containing 3% silica. Additive-free polyacrylonitrile polymers showed high ionic conductivity. These results seem promising for the use of the nanofiber membranes made of polyacrylonitrile polymer as a polymer electrolyte membrane in a fuel cell by acid doping. New studies are planned to examine and optimize the effects of acid doping parameters. You can see our study team for our work. Thank you for your attention.
Thanks for the nice talk. We needed to be on time. And if anybody have questions for our speaker, please type your questions through the chat, and you can directly move on to the next session. Can you please stop sharing? And we are going to do our next talk for Professor Kanupriya Sachdev from Malavia National University, National Institute of Technology, India. Is our speaker here? Whether we do talk on live?
Maybe we can play the video.
Oh, please.
Good morning. This is Kanupriya Sachdev, and it's morning in India now. And I'm going to present my oral presentation on synthesis and characterization of few layer pristine and nitrogen doped CVD graphene for supercapacitor application in this International Conference on Advances in Functional Materials 2021. So this is the outline of my presentation. So basically, I'll be talking about the experimental work which we have done and the results which we have received from this experimental work and certain conclusions. So graphene is already a well-established material for the supercapacitor application, given its large area and extraordinary functional properties. And doping a heteroatom in this graphene is a very effective way of enhancing the electrochemical performance of graphene. So this is the idea we have taken, and normally the researchers have used ammonia as the source for doping in graphene, but considering the hazardous nature of ammonia, we have used nitrogen replacing the ammonia in this work. Okay, so this is the diagram which gives you the device fabrication which we have done, and the two anodes are the CVD grown graphene, the pristine as well as the nitrogen doped, and then we have the this is a sodium ion capacitor device where we have NaClO4 PVA hydrogel membrane as the electrolyte as well as the separator. So this is the method which we have used to grow the graphene, the pristine and the doped. So in case of, as I said, in case of the ammonia is used as the source of carbon in the graphene, and the argon gas and the hydrogen gas, they are used for annealing the copper substrate for 180 degree before the growth phase at a rate of 100 and 50 SCCM per minute respectively. We have taken polished and HCl treated copper substrate as a catalyst in the process. The methane gas was used as the carbon source along with the hydrogen gas at the rate of 25 and 50 SCCM respectively. The growth of graphene was allowed for 35 minutes, maintaining the chamber pressure at 150 torr and the temperature at 950 degrees centigrade. The samples were allowed to cool down to the room temperature inside the furnace. So this is the process for the few layer growth by the graphene, and the optimization of the processing conditions gives us the control over the number of layers which we get in the pristine graphene. And for the doping for this graphene, we had introduced the nitrogen gas as well. Once these pristine and the doped graphene layers were grown, they were transferred to the desired substrate, and this was the usual transfer process using the PMMA, we had done the transfer of these few layer graphene on the desired substrate. So after getting the sample, we use the characterization techniques to verify the about these samples and to get the information about them. So this slide shows you, it gives you the field emission scanning electron microscope images of the CVD grown graphene on the copper substrate, and this one gives you the nitrogen doped graphene on the copper substrate. At the lower side, the EDS spectra of the pristine graphene and the EDS spectra of the nitrogen doped graphene sample are given, and we can very clearly see the presence of nitrogen there. The peak shows here gives you the presence of the nitrogen there. So the EDS spectra confirms the growth of the desired samples. These are the high resolution transmission electron microscope images of the CVD grown graphene sample, and the inset gives you the SAID pattern, and the SAID pattern is quite giving you the hexagonal pattern which gives the crystalline nature of the grown graphene. Then we also checked that what is the number of layers which we got in the sample, as we wanted only a few layers there, and these are the Raman and the UV visible spectra for these samples. The peaks, the characteristic peaks of the graphene, which are the D band, G band and the 2D band, when we calculated the ratio of the ID and IG and the ratio of I to D and IG, then we could see that the number of layers in case of the pristine graphene was up to 5 layers, and for the nitrogen doped graphene it was 3 layers. And then this is just the UV visible spectra of these two graphenes. Checking the thermal stability of these samples, we found that the nitrogen doped graphene, which is shown by the red curve, it is a more thermally stable sample, so naturally a better characteristic for the electrochemical applications. Doing some Hall measurements on these samples, we found that the nitrogen doped graphene had a better conductivity, and the mobility also was increased. We can see it's almost 3 times the mobility in case of the pristine graphene, and this leads to a very good conductivity, increase in conductivity of this graphene. So the nitrogen doping has been found usually by the researchers to increase the conductivity of the samples, and we found the same. So these are the now checking the electrochemical performance of these samples. These are the results of the cyclic voltammetry, and these are the cyclic voltammetry plot of the CVD grown pristine graphene showing the specific capacitance, and these are at different scan rates from 10 millivolt to 200 millivolt per second. Okay, so there's a typo here. This should be millivolt per second. And then we could when we check the cyclic voltammetry of the nitrogen doped graphene, then we could see that you can see very clearly that there is an increase in the area of the plot, and moreover the shape of the curve is giving moving towards a square shape, and it's not exactly the ideal EDLC behavior. It has some curve at the top, so that means there is some pseudo capacitance also showing in these samples. So the doping actually results in some pseudo capacitive behavior, and the combination of the two EDLC and supercapacitive behavior may increase in the result of the electrochemical performance. So these are the galvanostatic charge discharge curves of the two samples. The upper one shows for the pristine graphene and the lower one for the nitrogen doped graphene. Again, better electrochemical performance was seen by the nitrogen doped graphene in terms of the power density as well as energy density. the calculated ones. This gives you the electrochemical impedance spectroscopy, EIS behavior of the two samples, and the EIS spectra, the red one is for the nitrogen doped graphene. This plot, you can see it's quite steep as compared to the pristine one, and what we found was when we calculated the series resistance, we saw a drop in the resistance in case of the nitrogen doped graphene. So we can conclude that the number of layers which we got from the Raman spectroscopy, we could see that it's a few layer graphene sample. The high resolution TEM images show the transparency, very good transparency in these samples. The EDS spectra gives you the confirmation of the nitrogen doping there, although the amount is quite small. There were no impurities detected in the synthesized sample. The Hall measurements give the superior conductivity caused by doping, and quasi-rectangular shapes in the cyclic voltammetry indicate the introducing of the non-Faraday capacitance in the device accompanied by the pseudocapacitive region. The galvanostatic charge discharge gives an enhanced energy density and power density in the nitrogen doped graphene, and the nitrogen doping in the graphene results in a higher aerial capacitance due to the enhancement in electrochemical activity in comparison to pristine graphene. Thank you.
Thanks, our speaker. And we are going to move on directly for the next talk. And do we have a recording, Jin Yuan? Our next.
Sorry, the following two speakers, we don't have their videos.
Okay, so Michael Prouva from ESPCI France is our speaker here. Well, this is probably this is international. We don't have our next speaker. Then that would be the last speaker of our session. We're going to take a few minutes here. I see Divaka.
I'm here.
Okay, great, wonderful. So you could, we have 4 minutes, and you could share the screen in advance, but let's have a 2-3 minutes break, then get to your talk.
Okay, thank you so much. Thank you so much.
We have a few minutes before our last speaker. So this is opportunity. If anybody have questions to our speakers, you are welcome to type your questions through the chat. I believe like all the speakers are here, can answer your questions directly. So all the talks are short talks, and for most of them for 10 minutes or 15 minutes, and the speakers don't have a lot of time to directly answer your questions. The reach through the chat is a good approach on the restraint of this condition, and So I'm going to introduce our last speaker of this session, Dr.
Dibakar. Hello. Hello, I can hear anything.
Yeah, we can hear.
Shall I talk?
Yes, Dr. Dibakar, you can start your presentation.
Okay,
I
thank you
think
so
there
much.
is some-
Thank you so much.
Yes.
Okay, hello everyone. So I'm going to talk about the computational modeling of two-dimensional material for energy storage. So now we all know the necessity of research in energy storage. So now we are now here. If you see this plot, this is the world population versus the energy consumption, and we are now here. So at the end of this century, there will be enormous demand on energy. Okay, so this is a very important issue. That's why. But existing battery design has a lot of problem, and we recently saw a lot of accident, like Samsung, all the top companies, Samsung, Tesla, HP, Dell, say all encountered different issue, and most of this reason is the poor battery design. So we already know, I guess that the audience, we are familiar kind of the battery architecture. So just a quick recap. So we have the cathode and anode. So, and both cathode and anode, they are placed on current collector. So this is the current collector and this is anode. And we know that during charging and discharging, so we have the ion going this way and that way. So charging, discharging. Now the question is, what are the method of battery failure? Okay, so now if I do a schematic, this is the battery, and if I do a schematic here, so this blue dot, if you see, these are the active material, which can be silicon, selenium, whatever, and this purple, these are the polymer binder, which bind the active material, and this yellow is the current collector. Okay, so this yellow is the current collector. So what are the way the battery fails? So one is one of the failure is the interface failure, which leads to the electrical isolation. So how the interface failure works? So if I zoom this part, so I have the active material in contact with the current collector. Now during the charging, so we have the let's say lithium or lithium battery. In case of the lithium battery is lithium, or it can be sodium, magnesium, whatever. So it goes inside the active material. And during discharging, we have the other way around. So what happened during the charging, discharging? We have volume expansion and contraction. So because of that, there a lot of stress generated at this interface, right? So imagine, so this is a fixed surface, and this surface is volume expansion and contraction is happening. Then what will happen at the interface? There will be a lot of stress generation. So because of the stress generation, what happens exactly? So this at the interface, we have the fracture and debonding. Okay, and this is we can call it as an interface failure between the current collector and the active material, and because of this the battery failure happened. So similarly, another interface failure is the active material and polymer binder. So this purple is the polymer and the active material, so they are binded by like this. Similarly, again during charging, discharging, we have this active material volume expansion and contraction. And so because of that, there's a lot of stress generated at the junction between the polymer binder and active material. And because of that lot of stress, and we have this the breakage of the polymer binder. And now you see, when the polymer binder, there is a breaking point, so we have the electrical isolation, and that also cause the battery failure. So we can classify this failure as an interface failure in the battery. And another mode of failure is the failure of the active particle itself. So like let's say in the silicon, in lithium ion battery, so what will happen during the charging and discharging? We have enormous volume expansion, right? So like silicon, we have 300% volume expansion. So because of that, we have also the fracture. So we can classify these two method of failure. One is the interface failure, another is the failure of the active particle. So now the question is how to overcome this issue. So we hypothesize that the 2D material can do magic here. So now again, here is the battery architecture. So now you see, so when this, let's say anode material is placed on this current collector, and if the junction between the anode and current collector is slippery, then the interface, the stress generation will be less. Okay. So this is what we can achieve that by inserting a 2D material. We'll discuss about it. And another thing is that to overcome the problem of anode material failure, we can replace the anode material, conventional anode material like silicon or selenide, with 2D material. Okay, so and we hypothesize that in that way we will not have capacity loss, and we'll get rid of many other problems. So first, let's discuss the interface failure and how 2D material can solve this problem. So now this is the battery architecture. So we have the anode on the fixed current collector. So typically in the existing battery, so existing battery, it works like this. So either silicon on copper current collector or silicon on nickel current collector. Okay, so these are the traditional in battery, we see these things. Now we say that, okay, now let's do one thing. So instead of directly putting silicon on top of current collector, so what we do, we took this 2D material here and we put 2D material here. Okay, so what we are doing here, that we are putting the 2D material. So instead of putting that silicon on the copper or silicon on nickel, we are putting a 2D material in between. So now if I do this thing, if this is the 2D material, so now my interface is no longer, I'm sorry, so the interface is no longer this silicon on directly on nickel, but if I put a 2D material, the interface is silicon on graphene. So now what will happen if we do these things? So we did some first principle calculation and we calculate something called Markov separation. Markov separation is kind of adhesion property. Okay, so more Markov separation, they are tightly connected. Less Markov separation, they are less connected. So if you see these things, so if I took silicon on copper, silicon on nickel, and silicon on graphene, and I take silicon on silicon, you see that when silicon is on graphene, the Markov separation is much less. But in other case, when silicon on copper or nickel, the Markov separation is more. And silicon and silicon, this is for comparative purpose, we see that also more than silicon and graphene. So what does it say? It says that if we put a silicon on a 2D material, the interface will work as a slippery surface. Okay, so now we can use this setup, and we did some Monte Carlo simulation. So if you see this setup, what we do, in one case we took silicon on top of silicon. In another case, we put silicon on top of graphene. Then we did charging discharging modeling. So in charging, what we did, we put the lithium is going in, and discharging, we took the lithium out. So if you see that at the end of discharge cycle, you see that when silicon is on top of graphene, it is working as a slippery surface, and you see that the interface, they are not, the adhesion is less, but here the adhesion is more. Then you compute the interfacial stress, and you see that, I'll not go much detail. You see that here the interfacial stress is high. This is the shear stress, but here the interfacial stress is less, right? So similarly, we compute the normal stress. We see that the interfacial stress is more here, but the interfacial stress is less here. Okay, so it means that if I put a 2D material, it works well. And then our experimental collaborator did some experiment. So they took one case silicon directly on nickel, and another case they took silicon on nickel, but in between there was a graphene surface. And they found that if you see this capacity versus cycle number, they found that when silicon on directly on graphene, you see the capacity retention, the black line. If you see the black line, the capacity retention after 150 cycle is more, okay, as compared to when there is no 2D material. And then we can compare us to the fracture surface. We see that when I put 2D material, the fracture is less. So moral of the story, we can use 2D material as a slippery surface. So another, I told the failure of active material. So I'll just quickly show one result that we can use 2D material itself as a anode material. Like here in this case, we use porous graphene network PGN as an anode material, and we did the theoretical calculation, and we saw that theoretically, if I use graphene anode, we can achieve 1600 milliampere per gram capacity, which is almost four times the conventional graphite. And it nicely matched with the experiment. So moral of the story, we can use 2D material as an anode material. Okay, so now currently what we are studying, we are doing different combination of 2D material, like mixing different 2D heterostructure. Now when you put 2D heterostructure, we cannot just randomly put 2D heterostructure. Like so first what we are doing, we are first studying which combination is more stable. Like if I take two different 2D material, and if I take different boundary condition and different stacking A and AB, we'll see that in one case it is stable, like this case it is stable, another case it is not stable. So it means that before energy application, we have to figure it out which is the most stable condition, which is the least stable condition. After stability analysis, we can take that for battery application, which is we are currently doing for various 2D material. Okay, so I'll skip that. So now in the future directions, is I'm ending, because we have more than 700 2D material theoretically. So if you do the permutation combination, we have billion different possibility. So the future direction is the application of machine learning, which we are currently developing a machine learning model, which so in the machine learning model, we are doing a lot of DFT analysis and as a training set, and then we are predicting the result with our machine learning model. This is some of the preliminary model, which you can see that we put 3D material on 2D material, and we are studying the interfacial energy, and in some case we got good match. In some case we didn't get good match because we didn't train with enough result, but this work is currently ongoing. So I'll just quickly summarize since my time is finishing. So the two story I told. So one is that the 2D material and 3D material interface. So if I put the interface in between 3D material and 3D material, so 3D 2D interface will dramatically reduce the interfacial stress, and it will improve the cycle life of the battery. Okay, and another case is the 2D material itself, we can use an anode material. Okay, but before that we have to study like which 2D material combination is more stable and less stable. Depending on that, we can use it for battery application. Okay, and I thank you for attention. I'll be happy to take any question.
Thank you. That's excellent talk. Anybody have questions? You may have opportunity to directly ask our speaker, and or you can type through the chat. And this is the last talk of our session in the morning.
You can email me whenever you want. Okay, thank you.
All
Thank
right,
you so much.
thank you. Okay, thanks everyone. We are going to take a lunch break, and then there are sessions starting at 1 o'clock. Thanks everyone for attending this session. And thanks all our speakers. Bye-bye.
Thank you so much, Dr. Hemai Zhang, for chairing our second session for today. So
thank you.
Now you can enjoy your lunch, and we will be joining after 1 hour, inshallah.
Okay, thank you.
Thank you. Thank you, Jin Gyeon. We are meeting after 1 hour. Now we have the lunch break. Okay.
Oh, okay.
So you can enjoy the lunch.
Thank you. I'll come back
for your time.
maybe
Okay,
15,
okay.
25.
Okay, thank you so much.